Hi everyone, a very good morning to all of you. Let me know if you can hear me. Okay, so I think everything is good, right? Cool. So, how are you all doing? Thank you for joining in again. So, today we are going to discuss network layer and transport layer, right? One thing I can say that after this session, you will not be finding any difficulty or any confusion in network layer or in the transport layer. So we will be discussing every possible detail, which means that if there is something that is implementation dependent, then we will discuss that thing. If there is something that is fixed, actually in transport layer, in particularly in TCP, there are few things which are implementation dependent. So we will be discussing all of the things if they are implementation dependent. If they are not implementation dependent, then also we will discuss. So we will discuss many things, and we will complete transport layer and network layer today. So let's just continue in this session. Let me before I start, let me know if there is any doubt from the yesterday session, or otherwise we can continue. Okay. So I hope everything is good, and let's get started. Right? Good. So in network layer, we have finished one of the topic, which is IP addressing and subnetting. I mean, sorry, not subnetting, but yeah, IP addressing at least we have finished, right? Now, today we are going to start subnetting. Subnetting means that we are going to see that how to divide a network into further networks. And similarly, we will see something called as supernetting. So we will see these two concepts which are related to subnetting and supernetting, and then we will see some other concepts in network layer, right? Okay, so let's just start it. Give me a second. Great. So let's just get started. Now we are going to start with the subnetting. What is subnetting? Let me just tell you. Suppose that you have a network. Okay. Suppose there is a network that you have, which means I'm representing a network, all the set of IP addresses with the pie chart, because it is very convenient to represent with the pie chart. Okay. So I'm representing with the pie chart. Suppose you have a network. Yes, I will also be teaching the application layer. Okay, Vishnu. So let's just be in the session, and let's finish all of them. Maybe application layer I will be teaching in the evening once the graph theory is finished. Okay, Arpan is saying, sir, I'm currently finished lecture 1. It is amazing watching okay, in 2x. So just came to thank you. Thank you so much, Arpan. So, Arpan, yeah, many of the students are watching it later. So, if you are also watching it later, that is completely fine. But if you watch it live, then obviously you can attend, you can have a feeling of interaction, and you can ask your doubts live. So it is good that you are attending live, but that's fine if you are attending it later also. I just request you to put a comment below the video instead of here, so that I get to know, and other aspirants also get to know. Because if you put the comment here, then the visibility is very less. Only I and some other students which are currently here will get to know. Otherwise, like if you put the same comment there, then also like many other students will get to know. Okay. So in subnetting, what do happen? Like we have a network, and then what we do, we say that we can divide the network into further parts. Sometimes we say that we can divide the network, like we just want to divide the network into two parts, that's fine. Sometimes we say that we want to divide the network into four parts, okay, or maybe the three parts. So in the three parts also you can do it. How? You can do it like this. And if some people say that you want to divide into maybe one more part, okay, which means four parts, something like this, then you can do it. If you further want to divide, then also you can do it. So you can have any level of division. If you further want to divide, then you can do it. If you further want to divide, then you can do it. I mean, it is up to you, right? So how to divide, let me just tell you. Suppose that you have one network which is, let's suppose, this network, okay. And in this network, what you are doing, you are basically saying that you have, let's suppose, some number of bits which are for the host ID. See, if you remember that if I say backslash 24 or backslash 20 or something, right? Then it means, if I'm saying backslash 24, that means that 8 bits are free to use, right? 8 bits are free to use. Okay, just a second. Yeah, so 8 bits are free to use, isn't it? If I'm saying that backslash 24, that means 8 bits are free to use. Now suppose out of those 8 bits I fix the initial 0, okay, then these are the 1 2 3 4 5 6 7. These are the 7 bits that are again free to use, but I'm just fixing initial 0. Then it means I'm dividing my network into two parts. One is basically having, Okay, let me redraw it again. So let's suppose I'm saying that initial bit is fixed, which is 0, then 1, 2, 3, 4, 5, 6, and then 7, right? I can have anything here. So it means I'm dividing into two parts. And then if I'm saying that this is bit is 1, and then 1, 2, 3, 4, 5, 6, 7, right? Then I'm dividing into two parts. Suppose I further want to divide, then you can do it. Then it will be 1, 0, it will be 1, 1. Suppose I further want to divide, then it will be 1, 1, 0, it will be 1, 1, 0, and it will be 1, 1, 1. Suppose I further want to divide, then you can do anything actually, right? Maybe I further want to divide this part, then it will be 1, 1, it will be 1, 1, 1, and then 0, 1, 1, 1, and 1, or maybe vice versa. Does not matter. You can write like 4 times 1 here, and then 1, 1, 1, 0 here, right? So that's how you divide. Now let's just see that how to actually do it using the questions. Okay. Okay, Siddhi is asking that good morning, sir. Sir, I am done with the studies but not scoring good in the mock. So looking forward to learn how to approach sums in the test, how to think on it. So can you just hold for the end? Like we will take these are preparation related question at the end, because in the between it will impact other students also. Okay, thank you, Subhadeep. Thank you so much. Arpan is saying yes, sir. The region to watch the recorded video is that I can skip the known part. Okay, great. Thank you so much, Arpan. So now let's just see how to do it using the questions and how to, like, why it is even needed. So suppose that that you have a network which is looking like this, which means you have a university, and in that university you have different departments. Now, if you recall from yesterday lecture, if I'm putting one router, it means I'm actually dividing the network. Suppose there is no router, which means suppose I'm not putting these three routers, and my network is looking like this, suppose. Okay, which means all of this are connected to router directly. Maybe these are interconnected using the switch, or maybe using the hub, or using the repeater, but only one router is here. Then in that case, what will happen? If that is the case, then you will say there is no subnetting. But to do subnetting, what you need to do, you have to actually physically put the routers, right? I will tell you the difference in subnetting and supernetting. In supernetting, you are not removing the routers. Okay, it's not like you are removing the routers. I will tell you what is supernetting. Supernetting is very logical concept, but subnetting is actually existential concept, which means you have to put the routers, then only you can do the subnetting. So you putting the routers, and can anyone tell me that how many networks are here currently? So you will say this is one network, this is one network, this is one network, because these are three interfaces, and because of these interfaces you will say these are the three other networks, and then this is one more network, right? This is the question that has been asked very latest in the GATE 2022. Now let's just continue further. Now tell me why we even need subnetting. Why do you think that we need subnetting? We need to put the routers. Maybe we want some security purpose, right? Maybe I want to maintain this electrical department, electrical engineering. Let's suppose E stands for electrical engineering. So I want to maintain this electrical engineering separately from computer science. Maybe for the maintenance purpose I want to do subnetting, right? Maybe for the security purpose. Security means that you want to say that, see, this particular department might not allow to access some of the websites, whereas this particular department may allow to, I mean, you may allow to access some of the departments. So basically you can implement some of the specific rules here. Like you can implement this as a firewall. So router can work as a firewall. So which means you can implement some specific set of rules. You can say that, see, let's use this router as a firewall for this particular department. Let's use this router as a firewall for this particular department. So basically these are the uses. These are the uses to I mean, these are the needs to implement the subnetting. Okay, and these are the uses of subnetting. There could be many other. One of them which is very much needed is maintenance. You want to maintain the different departments separately. You want to have the security, or there could be many other reasons for the subnetting. Okay, now let's just see one physical example, and let's just see that how to numerically divide any network into four parts. Suppose they are just saying the four parts, they are not specifying the size, so I'm just assuming that equal size. Otherwise you can assume any size, does not matter. But okay, four networks in equal sizes. Let's just say equal sizes. Okay, so what does this mean? You want to basically, this is one set of network in equal sizes, means you want to have finally something like this, right? This is your final aim. This is our final aim. Can you do it? Very easily we can do it. How? We can borrow we can borrow 2 bits. So I can say it is 0 0 0 1. This is 1 0. This is 1 1, right? Which means if I particularly talk about it, it is 192.168.9.11, and these bits are free, and then /26. right? This will be the IP address or maybe the network address of this particular network. Similarly, you can write the network address for everyone. So that's how you can easily divide, very easy. But let's make the situation little tricky. Suppose, I mean, in the gate also they have asked these kind of questions. So let's just see if we can solve these kind of questions. Suppose they say that here not equal sizes, but they also specify the size. So here the sizes are not equal. Okay, they want to divide into 3 sub blocks, but the sizes are not equal. Sizes are not equal here. Okay, so what you will do? Let's just see the requirement first. They are saying that they want the one sub block of 10 addresses. So they want one network one. Let me just write network one with the 10 addresses. Net one with 10 addresses. They want network 2. They want network 2 with 60 addresses. 60. They want network 3 with 120 addresses, right? So they want 3 network with these. This is the requirement where the sizes are not equal. Can you do it? Okay, let's just understand this problem at the very basic. So they want to have some division where 10, 60 and 120 is requirement, right? So let's suppose this is the network. Okay, I'm not even worrying about the IP addresses. Let me just check if I can do it. I mean, let me just see if I can divide into 10, 60 and 120. Let me just see that how many total IP addresses that I have here. It is /24, which means 8 bits are free, which means I have 256 IP addresses with me. They want 10, 60 and 120. Can you do it? Maybe you can put a partition here, something like this. Then you will say it is 128, this is 128, this is 128 and this is 128. Now one of the requirement is definitely fixed, right? One of the requirement is done, which is 120. 120 is done, so can I just cross this out 120? I mean, I'm just saying that I'm done with this. Okay, numerically, like what is the IP address, what is the what is the network address, what are the first address, what are the broadcast address, these things I will tell you. But let's just see the picturally that how it is going to happen at the first place. Then we can just put the dot 0 dot 1 here and there, right? It is very easy to put dot 0 dot 1s. So once, let's just do it picturally that how it is actually happening. Can I just cross this out and I can say that okay, this is done, I'm done with this, right? Let me know. Narmada, are you here? Devanjan, okay, so Vadeep, let me know, Siddhi, if you are getting these things. Now, what you need to do, you need to basically see the other requirement. This is 10 and 60. Now, can you give 10 from here? See this, if you further divide it, then it will be a problem to you. Reason being is that it will be 64 64 if you further divide it. So you cannot bring you cannot give like something like this. You cannot say that 120 addresses I can give from here, 8 addresses I can give to someone else. No, either you give 128 or you give 64. It's always like divide in half. It's never the divide in any choice that you want. If you want to divide it, it will be 64 64. So you are done with this, and let me call it network 3. Okay, I think there was network, yeah, there was the network 3. So let me just call it network 3. It is just a name, so don't worry about it. Now I am left with this chunk. I have these two requirements. Can you do it? Maybe you can do it by this. You will say this is 64, which is network 2, and this is again 64, right? This is remaining 64. Now they want in the network 3 or in the network 1, they want just 10. See, they just want 10. Now you have 64 with you. Can you give this whole to this network? Let me just say A. Okay, so can you give whole to this A? Yeah, you can definitely give, because their requirement is 10, you are giving 64, so they will be maybe happy, or they will be, I mean, at least they will not be sad, because we are not taking anything from them. If they are not happy, if they are like khadus, then they might not be happy, but yeah, at least they will not be sad. That's my guarantee. So you can definitely give that particular chunk to that particular organization, which is A. But let's suppose that you don't want to waste your IP addresses. Then what you will do? You will say that why to give this 64? Let me just give 32. Okay, I mean, since you can divide, so why to give this 64? So that's why you will not be giving the 64. Okay, you will be saying let me give half of it, which is here you have 32 and here again you have 32, but they just want 10. So can you divide it again into two parts, 16 and 16, right? Now it is 16 and this is also 16, and then you cannot divide it further because it will be a problematic situation. Then you can give it to A, right? Is this fine to everyone? Let me know. Okay, so that's how you can do subnetting. For any question you can do like that, right? I mean, first step one is to for you to draw a picture. Draw a pie chart. Okay, that is the first thing that you do, and then rest the fixing the IP addresses here and there can be done later also. Okay, so draw a pie chart and then you will be done. So let me see that what are the IP addresses now. Now this will be having, see, this will be having 0, starting with 0. This whole again start with 0. So this will be 0 0. Sorry, this will be starting with 1. So this will be, let me write here, this will be starting with 1. So it will be 1 0, right? And then this whole chunk will be starting with 1 1. Then this like whole chunk is starting with 1 1. Okay, maybe let me just copy this on the next page and let me show you slowly. So this whole thing will be starting with 1 1, right? Okay. So since this whole thing is starting with 1 1, you will say it is 1 1, right? It is 1 1. Then you divide into two half, you will say it is 1 1 1, it is 1 1 0, it is 1 1 0. Then you divide it again into two half, then you will say it is 1 1 1 1 0 1, this is 1 1 0 0, right? So this is 1 1 0 0. And then this is 64, 32, 16 and 16. So this is A, right? So that's how you can do. Let me know if you have understood this. Cool. So what are the IP addresses now? Like you can see the IP addresses from here very easily, which is 14.24.64. Oh, sorry. Is this visible? Okay, because of my video, I think it is not visible. Now I hope this is visible, right? Okay. So it is 14.24.74.0 /24. So you can quickly give the IP addresses to every organization. So basically, I mean, it is up to you how you want to approach this question. But yeah, in the subnetting question, you can definitely see this as a picture. Okay. So can you write the IP addresses? Yes. For A, the IP address was, this was, let me go here. For A, the IP address is the same as 14. You will say it is same as 14.24.74. And then you have 1100 for A, that is fixed, and then slash, I mean these 4 bits are I mean you are free to choose anything in this 4 bits, so that's why /28. For B, you can say for B it is, this is B, right? The 10 is fixed, which means 14.24.74.10 it is fixed. Then this is 1 2 3 4 5 6, then slash this is 26, right? Okay. For C, can you write it? I think we can write for C also, which is 14.24.74.0 and then 1 2 3 4 5 6 7 /25, right? That's how easily you can assign for ABC. So this is using a picture, but I will say that if you can do it directly, then also you can do it directly. Okay, cool. Now let's just continue. So basically, how to do it directly, let me just tell you. Okay, without using the picture. I mean, the picture is nice, but if you don't want to use the picture, then let me just quickly tell you how to do it directly. Okay. See, there are many ways to visualize it. Many ways to visualize it. Okay, you can visualize it any way. So suppose that this is the question that they are asking. So what is the IP address that is they have given? It is 14.24.74.0/24, and that is having basically 2 power 8, which is 256 IPs. Right? You list out all of your requirement in the decreasing order, which means you first give to 120, then you give to 60, then you give to 10. Why in the decreasing order? Because if you see that how we did it picturally, we first divided, we first divided into two parts, right? We said like this is our network, then we divided into two parts. Then first we are having a bigger chunk, then we will be dividing into smaller chunks. That's how we do, right? First we will be dividing into bigger chunk, and then we will be dividing one of the bigger chunk into more smaller chunk, like that, right? So whenever they ask you these kind of questions, always fill the requirement in the decreasing order. Always give, okay, to the organization which is requiring highest IP addresses. Always give, or always write in the decreasing order. Basically, let me just write it in that way. Always allocate in decreasing order. Okay, I hope that is fine to everyone. So Twinkle is saying, hello sir, I had a doubt in yesterday's question. Message you on Telegram. Will you please explain that question once? Yeah, definitely. So let's do it at the end. Okay. So there is one particular question regarding regarding CRC, right? Regarding CRC, that was the question and that we solved in the class. So she is having some doubt, so we will solve it at the end of the session. Don't worry. Okay, so you want to do it for 120, which means for the 120, how many host bit you need? How many host bit you need? Just write the host bit now. Okay, so once you write in the decreasing order, I'm doing it numerically without using the picture. So you can use the picture, no, not a problem, but you can do like this also. So let's just write the number of host bits. Number of host bits. How many host bits you require here? If you need 120, then 7 host bits. Here the 6 host bits. Here you need this is 10, which means I think 2 power 3 is 8. Okay, 2 power 4. 2 power 4 is 16. So I think you need 4. So you need 7 host bits here, and you have 8 host bits with you, which means what you will do? You will divide that into further for just one part, which means you will say this is 14.24.74.0 you will divide, and that is slash 24. And then since you just need 7 bits here, which means one of the bit you will be taking for the subnet. So here you will say like one of the bit you need for the subnet, which means it is already 0 slash 25, and then remaining is basically something like this, right? 74.0, sorry, not 0, it will be 0 1, which means so basically it is 0 0, like 0 you have given to this, and then it will be 1 basically, right? 1 means it is 128, right? 128 slash 25. Okay, so then using this you can divide that into further two parts. Okay, so you can take one of the bit from it, and then you will be having this, and then you can further divide this also into two parts, or maybe if that is required, then you can divide further into two parts, and then finally you will be having this as network 3, this as network 2, like that, right? So you can do it like in that way, but I will say that if you do it pictorially, then it is better. Okay, so you should be doing it pictorially. Cool. I hope you understood this. Now let's just directly do the questions, and let's see that what kind of questions are possible from this particular topic. Now, what they're saying, host X has an IP address this, and it is connected through two routers. Okay, this is the yesterday question that we had, that X is connected through R1 and R2, and that is connected to Y. Then they're asking how many distinct subnets are guaranteed to already exist in the network. So how many subnets are here? This is one, this is one, this is one. So 3 is the answer, right? Let me know if you have understood this. That kind of question we have already solved, and this is the very recent question that they have asked. See, they have asked this as a recent question. They have also asked the same question in 2008, but I think nobody noticed in the 2008. I mean, nobody noticed it earlier before the last year that these kind of questions has been asked. People were thinking that okay, this number of subnet kind of question has been asked only first time. Cool. Now, let's see this. What they're saying: an organization has a class B network and wishes to form subnet of 64 departments. So, subnets for 64 departments. The subnet mask will be, so number of subnets are given to you. Number of subnets is equal to 64. So how many subnet bits you need? See, this is the network bits. First you have net ID, network bits, and then you have subnet ID, right? And then you have host ID. So here you need 2 power 6, so which means you need 6 bits here. It is class B, it means it is already having 8 plus 8, 16 bits reserved. So 16 plus 6, 22 bits should be reserved finally for the subnet mask. So 22 means that this is 8 plus 6, 16, and then these 6 bits are reserved, which means in the subnet mask you will be having 1 1 1 1 1, 6 times 1 and 0 0, right? And this will be subnet mask. 6 times 1, which means 255 minus this is just 3, right? 3, actually it is 252, so it should be 252, which is D is the answer. Okay, okay, you didn't get the last question, this one. So here they are asking about the number of subnets. We have done this kind of question earlier also. If they ask you number of the subnets, then we will say each interface going from the router is actually one subnet. So how many subnets are here? 1, 2 and 3. Each interface is one subnet, right? So these are the 3 subnets that we have. Okay, I hope you understood. Now let's just move further. So here D is the answer. Now let's just see what they're asking as a next question. In a class B network, if the subnet mask is given is this, what is the maximum number of hosts per subnet? See, this 248 means what? How many ones are there? This is 128 plus 64, which is 192 plus 32. 192 plus 32, 224, and then plus, sorry, 192 plus 32. Yeah, okay. This is 2 to 4. Now, interestingly, they have said like this is plus 8. So basically, they have said that this is not contiguous. I mean, number of ones that you have are not contiguous. So it is not necessary to be contiguous. First of all, okay, in the subnet mask, you can have I mean, you can have ones in between also. So how many ones you have here? 1, 2, 3, 4, which means 4 are remaining. So basically, there are 4 zeros here, 4 zeros here, and 8 zeros here. So 12 total zeros. Number of zeros in subnet mask is equal to 12. Then what does this represent? If number of zeros in the subnet mask is 12, then it represents the number of host ID, bits in host ID is equal to 12, which means total number of hosts are 2 power 12. And since they are asking about the host, actually hosts are not 2 power 12, it is 2 power 12 minus 2. Reason being is that like the first address and last address are reserved. So that's why 2 power 12 is I think 2048, right? 2 power 10 is 1024. Okay, this is 4096. Just a second. This is 1, 2, 3, 4. Okay, I think this representation is wrong. 128 plus 64 is 192. 192 and 32 is 224. Oh, 224 and they have 8. First of all, this should be 4. So that's fine. No. Okay, this is 2 to 4. 2 to 4 and 248. They have 16. And then if you add 16, this will be 0. This will be 240 and then they have 8. Sorry about it. So they have this 1, 2, 3, 4, 5 ones, which means they have the 3 zeros here. Okay. So sorry about the representation. They have 3 zeros here. It means it is 11. See, these kind of silly mistakes can also happen in the exam, and if there is one option something like that, then it will cost us a lot, right? But in the exam, actually, we are a bit more conscious. Here I'm conscious, but in the exam, you are super conscious, right? So okay, you will verify yourself every calculation. So maybe it is very less chance that you will be doing that kind of mistakes in the exam. So it is 1022, right? So that's why. Sorry, this is 2046. 2046. That's why C is the answer, right? So C is the correct answer. Okay, cool. I hope you understood. Now these are the easy questions. Let me. Okay. Let's just do this question. This question has been asked in GATE 2019, very recent question. Let's just see that what they're asking. Consider three machine M, N, and P with the IP addresses these respectively. The subnet mask is set to this. Okay, for all of these three machines, which of the following is true? That they all belong to the same subnet, they belong to the different subnet, and so on, right? So they are asking this. So let's just see this question. M is having 100.10.5.2, N is having 100.10.5.5, and P is having 100.10.5.6. They are applying the subnet mask which is 252, which means only last two bits should not change. Okay, I mean last two bits are basically should not change, and everything last two bits can be changed and everything should be fixed. So basically, if you apply the subnet mask here, so it will say that last two bits, okay, here this 2 is getting represented by 10. So last two bits are 10 here. Here last two bits are 101. Last three bits are basically here it is 110. So and everything else here is 0, right? Everything else here is 0. Similarly, everything else here is 0. Everything else here is 0. So it is already same till this point. Already same till this point. Now you need to check that whether they belong to the same subnet or not. See, this subnet is saying that that everything should be 0, right? For this the subnet is saying everything should be 0, but this is 1, right? So that's why M and N are definitely in different subnet, but N and P are in the same subnet, because this is 1, this is 1. So you can say only N and P belong to the same subnet, right? Where is the answer? Yeah, only N and P belong to the same subnet. Let me know if that is clear. I mean, that was an easy question, so that's why I'm just doing it little faster. Okay, you just need to check last 2-3 bits. Cool. I think these questions are doable probably. Or let me check if there is something. The organization has approached the ISP. The ISP uses CIDR and then has IP address this. Okay, minimize the number of routing entries. Okay, let's just finish the route aggregation, and let's just see this question after it. Okay, once we will finish the route aggregation. Yeah, let's do this question. This question is little interesting, so that's why let's just do this in the class. In the subnetted class B network has the following broadcast address, which is this. Its subnet mask is necessarily this. Okay, so they are saying the directed broadcast address is given to you. It is 144.16.95.255, right? It is DBA. What is directed broadcast address? You have ones in host ID part. Okay, you have ones in host ID part, and zeros. I mean, definitely there are ones in host ID part, but you don't know what is there in the net. I mean, network ID part can contain anything. Okay, so if this is the directed broadcast address, then what? I mean, if for any directed broadcast address, what we do? We put to convert any IP address, to directed broadcast address. What we do? We put ones in host ID part and leave network ID part as it is, isn't it? So that's what we do. Okay. So now let's just see that what they are asking. A subnetted class B network has the following broadcast status, which is this. Its subnet mask is necessarily this. Okay. So they are asking about the subnet mask. So it is given that, see this question. This question is very, very nice question. They are saying it is class B network, right? Okay. Now they are saying a subnetted class B network, which means a subnetted, which means like they have borrowed some of the bits from the host bit. Now see, this is the subnetted class B address. So since it is class B address, I know that these bits are definitely fixed. Now from this 95 and 255, you can have something, right? So basically these bits are definitely fixed, which are part of network ID. These bits are part of network ID, that is for sure. So I will say these bits are part of network ID, right? These bits are part of network ID. Now let's just represent this 95 in binary. So can you tell me what is 95 in binary? Let me just convert using I mean the online converter. So okay, it is 10. So it is 10 and then 5 times 1. So let me just write it here. This is 10 and then 5 times 1. Okay, so this is 95 in binary, and then 255 is basically 1 2 3 4 1 2 3 4, right? So this is 95 in binary. Okay, now what we need to do, we need to check which of the bits are part of subnet ID. Now what we do to convert, what we did to convert it to directed broadcast address, wherever I had the host, I just put it to 1. And if it is 0, then what it means, it must be part of subnet ID. isn't it? It must be part of subnet ID. It also must be part of subnet ID, because if it has been the host ID, then I must have one here in the director broadcast address, right? Is this clear to everyone? It must be, it also must be part of subnet ID. Let me know if this is clear to everyone. Now what they are saying that you have ones in other places. I mean, few other places you have ones. Now tell me here, can you say that it is a part of host ID or subnet ID? See, it may be a part of host ID, it may be a part of subnet ID. That is the problem, that you don't know actually. Why you don't know? Since it is 1, now there are two cases. Either earlier it was 0, you converted that to 1, which means it was part of host ID. You converted to 1. Earlier also it was 1, right? I mean, see, they have given that this is the directed broadcast status. They have given this is a directed broadcast status. Now, how you have converted some IP address to directed broadcast status? Maybe wherever you had zeros, you must have put ones, right? So if it is zero, I mean in the host ID part, if it is 0, then it must be a part of subnet ID. If it is 1, then you don't know that whether it was a part of subnet ID or it is not part of subnet ID, right? Which means there could be two cases. I mean, you must have, see, to convert something to directed broadcast status, what you did, you must have taken some IP address, right? Okay. So what you did, I mean, let's suppose, let's go back in time, okay? Let's go back in time and see how you have arrived with this particular, and see how we have got this particular directed broadcast address. Let's see. Let's see that how we have got this directed broadcast address. Which means what I must have done, I must have taken some IP address. Okay, I must have taken some IP address. Maybe something like this. Maybe I don't know basically, right? Maybe like some IP address. I must have taken some IP address, and then IP address from that subnet, and I said like, okay, see, this is the IP address, and then I must have said that let me put ones in place of host ID, right? That was my process. Now your IP address, and then finally you got this, right? Finally you got this basically. So basically you are saying that you must have done some manipulation, which means you are saying that you must have put ones in the place of host ID, and you have got it, right? So wherever it is 1, it may be host ID, or it may be earlier also it was 1. You see, either, see, let's suppose that the IP address that you are taking, okay, it must be a part of subnet ID first of all, right? These two are you are sure, these two are you are sure, but you are not sure about something else. Which means if this is 1, okay, see here, these two could be like, I mean, these two has to be 0, and then let's leave this particular bit, and then this is also 0, that is fixed. But here it could be 0 also, right? This is, you don't know whether it is, like, currently you don't know whether it is host ID. I mean, looking at this, you don't know whether it is this bit is belonging to host ID or this bit is belonging to subnet ID, right? This bit belongs to subnet ID if in the like, I mean, the first address of that subnet, if it is 1. So yeah, just a second, let me think that how to convey this. See, this is 0, that it means, that is for sure that from wherever you have converted it, it must be 0 only. I mean, if you are not converting this 0 to 1, it must be the subnet ID. If you're not converting this 0 to 1, it must be a subnet ID. If it is 1, then earlier it could be 0, or, and then you have converted that to 1, which means this was part of host ID, this bit could be part of host ID, and that is why from this 0 you got this 1. Or maybe this bit part of subnet ID. The second case is this, where this bit is part of subnet ID, dot, then you have this is 0, and then this bit could be this bit could be 1, right? Could be 1 earlier also, it could be 1, and this is part of subnet id. See, subnet id you leave it unchanged, right? To convert into directed broadcast address, subnet id you leave it unchanged. See here, to convert any IP address to directed, we put once in the host id and leave and network id as it is, okay, or the subnet id as it is. So basically earlier also it was 1, you left it as it is, it means it was a subnet id, or earlier it is 0, okay, it was a part of host id, you converted to 1. So there could be two cases. So wherever it is 1, you don't know whether it is a part of host id or it is a part of subnet id, right? So let me know if you have understood this, if there is any doubt here. See, how to convert something to a directed broadcast address, wherever, whatever bit you know that it is a host id, okay, whatever bit you know, it does not matter whether it is 1 or 0 in a particular IP address, okay, it could be anything, whatever bit you know, okay, let's suppose this is a host id, this is a host id, this is a host id, whatever bit you know, you just put once here, okay. So if it is 0, then also you put instead of 0 you put 1, okay, which means you convert it like this, right? Let's suppose if this is the host id, then basically you convert it to 1, this is a part of host id, then you convert it to 1, okay. So yeah, this is, so see here, if it is host id, let's suppose these are the host ids, if it is 0, then also you convert it to 1. If it is already 1, that then I mean host id you will be keeping it 1. If it is already 1, then also it is 1. If it is 0, then it is 0. So sorry, then it is 1. So basically in place of host ids all are 1, and wherever is the network id, whatever is the network id, you leave it as it is, whether it is 0 or it is 1, right? So in place of host id, you will be writing 1. If it is network id, let's suppose it is a part of network id, you leave it as it is. It is a part of network id, you leave it as it is. It is a part of network id, you leave it as it is, right? So these are the network ids. So maybe I can use a different color here, okay. So let's suppose this is the part of network id, you leave it as it is. This is the part of network id, you leave it as it is. This is a part of network id, you leave it as it is. So basically for the network id, you leave it as it is. Now, looking at this one, you cannot say, see, looking at 0, you can definitely say it is a network ID, but looking at this one, you do not know whether you left it as it is or you converted the host ID to the one, right? Looking at the one, you cannot say. Yes, Aman, discrete mathematics is completely free. So Aman is asking, sir, discrete mathematics completely free hai kya? Yes, you can watch the discrete mathematics completely. It is one of the best course at Go classes. You should definitely watch it. Those who have watched it can definitely say that it is one of the best courses of the Go classes. Although all the courses we are I mean putting our best efforts, but particularly discrete mathematics is favorite to Deepak. So that's why Deepak, I mean for the digital also, or for the compiler for other subject also we have put the best efforts. But it was earlier it was used to be favorite for the Deepak, so he has put a great efforts in discrete. Okay. So let me know if that is clear. See, looking at whatever IP address you had, if it is a host ID, you must have converted. If it is 0 or 1, does not matter. Okay. If it is 0 or 1, let's suppose these are the host IDs. This is host ID, host ID, host ID. In place of host ID, you always have 1, right? If it is 0 or 1, does not matter. You just write it 1. But if it is subnet ID, you leave it as it is. Now, looking at this one, you don't know. Looking at this 0, you can definitely sure that you left it as it is. That's why it is 0, right? But looking at the one, you don't know whether it was a part of the subnet ID, which means this one. See, there is no difference in this one and this one. Can you look at this one and can you tell whether it got converted from 0 to 1, or maybe it is a part of host ID or it is a part of subnet ID? So you cannot say this, right? So that's why I will say that looking at the one you cannot determine. So here looking at these ones you don't know, but for these two bits you are 100% sure. So now they are saying that what is the network mask? Okay, so this question is extremely interesting. Now this is the directed broadcast address, and from this directed broadcast address, first let's just determine what are the subnet IDs. Okay, so from this directed broadcast address you can say the subnet IDs are these two, and for this bit you don't know. For this bit, you don't know. Similarly, for other bits also you don't know, right? Only for these two bits you know. Only for these two bits you know that these are the subnet IDs. Now, you want to convert that to mask, right? Subnet mask. So, wherever is your subnet ID, you just put 1 there. So, which means this will be 255. Wherever is subnet ID, I mean, which is subnet ID, you put 1 there. This is 255.255. And now, see, this is subnet ID. You will be putting 1 here. Then you don't know this, okay? You don't know this. This is subnet ID. You will be putting 1 here. You don't know this. You don't know this. You don't know this. You don't know this. 1, 2, 3, 4, 5. You don't know this. Dot. You don't know any of this. Okay. So any of this blank you don't know. So the subnet mask will look like this. If it is part of, let's take a case where, let's suppose this is a part of subnet ID. Then you will put 1 here. If let's suppose this is a part of host ID. Okay, let's take a case where this is a part of host ID. Since you currently don't know, that's why I'm taking two different cases. If this is a part of host ID, you will put in 0 here. So here it will be 1 or 0 depending on that particular bit is subnet ID or host ID, right? But since you don't know, so that's why I'm leaving it as it is. Now any of this bit can be filled with 0 or 1 because we don't know the enough information. We don't have enough information. If somehow I come to know that okay, this bit is a host ID, then I will put 0 here. If somehow I come to know that this bit is a network ID, then I will put 1 here, right? But currently I don't know, so I'm leaving it as it is. Now tell me, looking at here, tell me how many possible subnet masks are there? Number of possible subnet masks. What do you think? How many possible subnet masks are here? See, you don't know this. There are 5 bits you don't know here and 8 bits you don't know here. So 8 plus 5 is 13. So 2 power 13. 2 power 13 subnet masks are there, right? Okay, let's see the options, what they are saying. So in the options, I must be having these 2 bits as 1. Okay, anything else is possible. Anything else is possible. Actually, there are 2 power 13 subnet masks are possible, right? So let's see the options. So now let me just paste it here. This is the subnet mask that we are getting. Now I don't know this. Let's just see this. This 224 is saying this is 128 plus 192. Okay, plus 128 plus 64, which is 192 plus 32, right? So basically this 224 is 128 plus 64, 128 plus 64, which is 192 plus 32, and then yeah, so this is 224. So this is 224, right? Now tell me, is this a valid subnet mask? Do you have, so don't worry about anything else. Do you have these 2 bits, which is 128 and 32? Do you have 128 and 32 factor here? This should be 255.255 first of all. Do you have 128 and 32? Yes, you have. Then this can be subnet mask, but they are saying is necessarily this is subnet mask. No, necessarily this is not subnet mask, but this can be a subnet mask, right? Similarly, just see here, this is 240, which is 128 plus 64 plus 32, which is 224 plus 16, right? Plus 16. So can this be a subnet mask? Yeah, definitely, because I am just looking for these two numbers, 128 and 32. As long as I have 128 and 32, I can say it is subnet mask. At the remaining places, they are saying that these two are actually the network ID, maybe the network ID, maybe the host ID. I actually don't know, right? Can this be a subnet mask? Let's just check. Can this be a subnet mask? This is plus 8 also, right? Yeah, this can also be a subnet mask because it is a plus 8. But they are saying is necessarily. Necessarily is not true. So this either A, this is B, this is C. Yeah, A, B, C can be a subnet mask, right? So I am just looking for 128 and 32. As long as I have 128 and 32, I will say it is a subnet mask. Okay. So Pushpesh is saying, sir, I don't get that how the zeros in between of two ones can be a part of subnet, can be a part of host ID. See, it is definitely possible, although it is not very general, okay, but it is definitely possible that whatever IP address you have, okay, let's suppose this is 25.32, dot, I mean any IP address that you have, then it is definitely possible that this is 1 2 3 4 5 6 7 8, similarly dot 1 2 3 4 5 6 7 8. Then you can choose any of the bits. Generally we choose from the beginning, okay, generally we choose the contiguous bits. Generally we say that these are the subnet ID. Now these bits are from the subnet ID, but it is definitely possible to choose any arbitrary bits, okay, as a subnet. So let's suppose initially this is the complete network that I have, and I want to do a subnetting on this network. So to do subnetting, what we need to do? Let's suppose I need to divide this. Can you divide it into 4 different parts? You will say yes, definitely. You will do 0 0 and then 0 1 1 1 0 1 1. I mean, like that you will be dividing, right? Four different subnets basically. You can definitely divide using 4 different subnets using the method 0 0 0 1. But that's not very necessary to choose these as subnet ID. You can choose these others also subnet ID. You can choose one of this and one of this. You just need two, right? You can choose these two as a subnet ID. No one is stopping you. There is no rule that you have to do it. I mean, from the beginning. But for our convenience, we do it from the beginning. Okay. I mean, for the maintenance purpose, that if someone is having, let's suppose some ISP is having a lot of IP addresses and they want to allocate the IP addresses, but for the maintenance purpose, we do it from the beginning. But it is not 100% requirement that we do it from beginning, right? Okay. So we can have any subnet ID. I just need two subnet ID. I can have anywhere. Okay. We need two subnet ID. We can have it anywhere. We can have 2 bits as subnet ID from anywhere. Okay. Cool. Now I hope that is understood, that they have given. That was very nice question, and on the gate overflow, no one has answered it that nicely. I mean, they are considering from the leftmost. See, this is the common mistake. This is the misconception actually. I will say not misconception, but not, I mean, they do not know the broad concept. Broad concept means need not to be leftmost basically. Subnet IDs need not to be from the beginning. Subnet IDs need not to be. No one is, in fact, in the gate, this is not just one question. There has been many questions, I think, right? Has anybody solved any other question in the gate? I do not remember the year, but there are questions in between. They have the subnet IDs from the between. Okay, just let me know if you have solved that kind of question from beginning. Okay, thank you for space. So now basically this was extremely nice question where they have given a directed broadcast address, which means in the directed broadcast address I leave the network ID as it is. I convert the 0 to 1 for the host ID. Now if it is 0, then it must be a part of subnet ID. If it is 1, then I don't know whether I converted this 0 to 1 or it was a part of network ID where I left it as it is, right? So I don't know. I'm actually confused for the ones. So that's why whenever I have, okay, so whenever I have this as 1, so earlier it was 1, so I don't know whether this bit is a part of subnet ID or not. So but I know that this is definitely a part of subnet ID. If it is a part of subnet ID, in the mask I will be having 1. If it is a part of network ID, in the mask I will be having 0. Okay. So what are the total number of subnet masks are possible? I mean, this is the structure. So since the 30 bits are ready to free, so 2 power 13 subnet masks are possible with the given information that you have. Okay, they are just having 3 subnet masks in the answers, but there are actually 2 power 13 subnet masks are possible. Okay. So Badip is saying that he did the same approach as given as in the Go, but he just got to know the new thing today. So see, one thing I can say, like that I used to do at the gate overflow also. Whenever you see any answer that you think that you can actually add something, okay, then always put a comment or put an answer in Geo. Reason being is that your concept will be clear. Yesterday we were discussing about CRC, right? In the CRC, I completely discovered all of the things at my time of preparation. I put it on Go. So my things got clear. Later, many aspirants also thank you. Okay. So if you get to know something, and like from this video, if you get to know also, then you can just also cite that video that you for the detailed explanation was this video, and then you write your own text. That way you will be getting how to write an answer. Okay, the answer writing skill is also very necessary to I will say it is actually bonus point for you everywhere. I mean, you join any company, they will ask you to write the documentations. It is always a bonus point to convey your point to others. Okay, cool. I see sometimes many of the questions that I wanted to write the answer now on the Geo, because I know that this answer can be improved. But trust me that I and Deepak are too much busy in creating the video content that we do not get a time to write answers on Geo. We rarely get a time. So otherwise, there are many questions that I want to edit on the Geo, and I want to write the good answers on Geo. But it will be done. It will be done in next 6 to 7 months. Okay. Now, let's see very important and very nice topic, which is supernetting. Okay. So before supernetting, we need to know that how the router actually forward the packet. Okay. So Narmada is asking why 13, 14. It should be 14. Okay. Let me just see. Yeah. Okay. 6 plus 8. Yes. This is 6 plus 8. This should be 14. Okay. This is a mistake. Yeah. This should be 14. 6 plus 8. I agree. Cool. Now, let's just see that how to forward a packet that comes to a router, which means let's suppose that there is a router that is connected to different interface, different organizations, different networks basically, right? Which is having this router is, let's suppose, having connected with 4 different networks. Now, suppose there is some packet that M2 wants to forward, I mean this network wants to forward to this router, and then this packet has to be delivered here. Then how do you deal with this situation? Now, suppose that packet address is let's suppose from this network. From this network, I'm picking a random IP address. I mean that is coming as a source. It is coming from this, and as a destination, it is going to this. Okay. So let's suppose that there is a packet that is coming from one of the IP address and is going to another IP address. So suppose that the destination IP address I'm writing directly, which means let's suppose the destination is this 10201.4.22. Let's just pick any random address here. This is /24, so I can pick anyone, maybe .90. This is the destination address that I have. Now this packet, okay, packet with this destination address, has arrived to this router R1. Now R1 has to decide that this packet should be forwarded here, or should be forwarded here. Once you understand the concept that how the routing has been actually done, then the supernetting is very easy. Supernetting is just a byproduct of this. Okay. Okay. Now, thank you, Ratul. Thank you so much. So, Ratul is saying that watching recordings of yesterday's lecture, absolutely amazing. The way you have covered everything in a small amount of time. So, thank you so much, Ratul. And if it is possible, just put the same comment there on the video so that others also get to know. I mean, we also get some visibility, right? So, see, like why I'm saying it from 2 3 days, like again and again. I mean, not again and again, but why I'm mentioning it so often. Reason being is that if you see any random video, I mean a video which is even telling the wrong concepts, okay, and then I mean they are destroying destroying the concept completely, and then you will see the 1,000 comments. I can show you many videos which are not standard, which are basically teaching wrong concepts and which are conveying the concepts in wrong way. So there are 1,000 comments thanking them, and I'm just like my mind just get blown away that I mean what is happening with India. Like there are many creators which are teaching wrong, and there are many students that are understanding wrong and then thanking them. Maybe the students doesn't have any fault, but yeah, I don't know which fault is that, but yeah, that is okay. So that's why I'm saying that if you put the comments, then others also get to know the video quality. Okay, suppose this destination is coming to this router. Now how router R1 forwards to other networks? Tell me how router R1 forwards to other networks. It will consult with the routing table. So let's just see the routing table. Let's suppose this is the routing table it has, right? Now let's just understand this routing table, and then you will get to understand the supernetting very easily. Suppose this is the routing table that it has. I hope that is visible. Okay, or otherwise I can write the routing table here. This software is very nice, right? Okay. So you just see that if this destination is coming to it, now it will check whether it should belong to it. How it will check? It will apply this subnet mask which is /26 to this. If you apply /22 to this, then you will not be getting this 180, right? So definitely it should not forward to M2. Definitely similarly not to M0. And then if you apply /24, then you will be getting this. You will be getting this. Then maybe M3. If you right, why I'm saying maybe, you will get to know. If you apply /22, then let's just see. If you apply /22, which is to not 1.4.16.0. Okay, so if you apply this 22/22 to here, then what you will be getting? I hope you are getting what I mean to say, right? So here the destination IP address which I'm getting is this. Now I need to apply /22. /22 means that if you apply /22, then you will be getting /22 means 22 bits are fixed, and then you need to change remaining 10 bits. So basically here this is basically 8 and 8 16, and then 6 bits are also fixed. 6 bits means that, let's just check, this 28 or 22 will be basically from 16, right? 16 plus something, right? 16 means that it is basically holding the position which is 8 4 2 1, 2 power 0, 2 power 1, 2 power, this is 1 2 3 4 5. So okay, 6 7 8. Now basically 6 bits are fixed. So 6 bits are fixed, then it means 1 2 3 4 5 6 7 8. So basically this is 3 4, and then 16 means 22 means, okay, let me write it. 16 plus 6, 6 means 4 plus 2, right? 16 plus 4 plus 2, 16 is this, and then 4 means 2 power 0, 2 power 1, 2 power 2, 4, and so this is 22, and everything is 0. Everything is 0. Now you need to check remain like initial 6 bits, 1 2 3 4 5 6. So initial 6 bits should be as it is, and then you convert that to 0, right? So what you will be getting, let me just write it here. What you will be getting is this. It is 0 0 0 1 0 1. This is fixed, and then you will be converting this 10 to 0 0 0 0.0, right? So now let's just check whether this is same as what I have here, which is 16. Am I having 16 here? Obviously no, right? Since this is not 16, so that is why, like see here, this is 2 power 0, 2 power 1, 2 power 2, which is 4, 2 power 3, 2 power 4, 16 plus 4, which is 20. So this is not 16, so that's why it is not matching with this. So it is matching only with 1, so that's why it will forward to M3. So that's how it works. If the destination address with that IP address is coming, with this IP address is coming, then it will forward to M3. Now you know how the forwarding works, right? Okay. So if this destination address is coming, then forward it to M3. Now let's just check that how to do it. If there are multiple matches are there, then how to do it? So it might be possible that there are multiple matches are there. So let's just see, and that's the origin of supernetting basically. So let me first know that if the forwarding of IP packet is clear to everyone. Okay, let me first know that if the forwarding of IP packet is clear to everyone. If some packet is coming to this router, it will consult the routing table, and based on this, it will forward, right? Whichever it is matching. Now, let's see a situation. Let's see a situation where this router is basically connected to this router, and this router is connected to 4 organizations. Now, can you write a routing table? Can you draw? Okay, can you draw a routing table for R1, and can you draw a routing table for R2? So my question is that if that is given to you, then can you write the routing table for R1? Similarly for the R2. Okay, actually that's very easy. What you need to do, you can just convert it. I mean, you can just say that, see, if it is slash 26, then go to, if it is this organization, go to M node. If this is this organization, go to M1, so like that, right? That's very easy. You can definitely write the routing table for R1. So let's suppose this is the routing table for R1. Now, can you tell me what is the routing table for R2? That's very interesting question. Once you understand it, your supernetting will be clear. See, now let's just write, this is routing table for R1. Let's just write routing table for R2. What it will be? See, there is a big misconception about the supernetting. We are going to clear that myth. Have you heard of that rule? Okay, let me just tell you the misconception. Actually, like, to tell the misconception, I should also be knowing the misconception, but I do not remember those rules, so-called rules, supernetting rules. That actually I do not remember, but I think first address something like that, right? I mean, these are the misconceptions. That's why I prefer not to remember these things. First address should be divisible by a number of divisible by number of IP addresses, something like that, right? Number of subnets. I don't know. Actually, I don't know, but yeah, there are some misconceptions, right? There are some so-called rules. Okay, there are some so-called rules. Now, can you give me any single reference that these so-called rules are standard? Like, I have tried my best in the last year and I have not found any standard resource. I have found one Geek for Geeks article, but that is obviously not a standard. Any student can go and write there. So let me know first, have you heard of these misconceptions that there are some rules, supernetting rules? In fact, in GATE, there has been questions that actually break this myth of the supernetting rules. So I don't know from where those supernetting rules are coming. I mean, all the coachings are teaching some supernetting rules, and from where these supernetting rules are coming, that also I do not know. Let me know if there is any standard resource you find for these supernetting rules. Okay. So let's just see that how does the supernetting works. Now, like, I will tell you why these rules are not making sense. I mean, these rules are good, but it is not necessary to have these rules to be followed. Okay. So let's just check that what is the routing table for R2. If this is the routing table for R1, then I will say the routing table for R2 will look like this. This is the routing table for R1, and routing table for R2 will be something like this. This is, let me write it, this is R2. Okay, and everywhere you will be writing just M naught. Okay, this, let's suppose this is M naught. Everywhere you will be writing M naught, right? M naught, M naught, something like this, isn't it? Everywhere we are writing for M naught. Now, yeah, Siddhi Singh, this is the first point that I have in my notes. Everyone has in their notes if you have studied from some coaching. Okay. So, but these are not. I mean, just tell me a standard resource, then I will agree with you. I have not found that in any standard source. In fact, I found the counter examples. So that's why I'm convinced that these are not any rules. I will give you the counter example. I will tell you the standard source of the counter example. Okay. So in the Tannenbaum, it is clearly written that it is not need not to be contiguous. See, one thing is also written here that they need to be contiguous, right? Need to be contiguous. In Tannenbaum, it is clearly written that they need not to be contiguous. In Tannenbaum, like, I do not have a screenshot, I think, currently, but yeah, in Tannenbaum it is clearly written. Anyway, I will come to that. Let me know if the R2 routing table is clear to everyone. Okay, we are following sort of time, so let's just continue. R2 routing table is clear to everyone. Do you see any redundancy in R2 routing table? What is that redundancy? It says that, see, if you want to forward to this, then go to M naught. If you want to forward to this, then go. This M naught is coming again and again, right? This is very much redundant, and that's where the supernetting comes into the picture. Okay, that's where the supernetting comes into the picture. It says it is just a logical idea. Okay, so here the R2 routing table is looking like this. Let me know if everyone is clear with this R2 routing table, because if you are not clear with the R2 routing table, then you will not be understanding things about the supernetting much. It is very easy. See, I just told you the R1 routing table. I am saying that this is the R1 routing table. Based on this, I am just asking you to make the R2 routing table. I am saying that, see, you can make the R2 routing table just like that. If any of this organization, then using the R1 routing table, you will say, okay, it has to be go to R1, which means M0 everywhere, right? Now, let's just check what we can do for this R2 routing table. Since it is too much of redundancy, then I will say that, see, you are anyway going to the same, then why not I just say that, okay, let's just combine all of this and let's just have only one entry. Okay, default will be obviously there, but for these four, let's just have only one entry. Let's just have only one entry, and here I will be saying something. So R2 routing table, I want R2 routing table to look something like this. Okay, after supernetting, it will be something like this. Actually, I just want one more entry here. Okay, and that's what I'm looking for. There is one more entry I want, and this will be M0. So this is after supernetting. This is the idea of supernetting. Now, what to do to combine all of this? Is this a physical router removing or router putting or something like this? No, right? It is just a logical idea that we do in the supernetting. Now, for that, what we will be doing, we will be saying that let's just examine all of these networks, and then since the interface is common. See, one thing which is very important about the supernetting is that interface must be common. If this is M1, this is M0, you can never do the supernetting for these two networks. Okay. So the interface must be common. This is the first criteria. Obviously, if the interface are different, let's suppose this is M0, this is M1. For this network, can you combine these two networks? You can never ever combine these two networks. If the interface is common, then only you can combine. Then only it makes sense to have one routing. I mean, you can shorten your routing table, right? Supernetting is just a shortening your routing table. Just shortening routing table. Now, let's just see that how to do the supernetting for here. Now, if the interface is common, then only you can do first of all supernetting. But let's just see that, let's suppose the interface is common in the example is as previous, and let's just see now how to do the supernetting. What will I check? Okay, first criteria must be satisfied. Again, the interface should be common. Every of this network are connected to the same interface, which is M0. Okay, see here, every of this network are connected to the same interface, which is M0. This interface, this one, which is M0, right? Every of this network. Now, with respect to R2, it is just M0. Yeah, with respect to R1, you can never do supernetting. Tell me, can you do the supernetting at R1? This is a routing table for R1. Can you do the supernetting for R1? Let me know clearly. Obviously no, right? You can do the supernetting for R0 or for R2 only. For R1, you cannot do the supernetting. I hope that makes sense. Now, let's just continue. And what I was saying, let's just see that how to do actually the supernetting. So these are the four networks which are connected to M0 only with respect to R2. Okay. Now what you will do, you will check this particular IP network. You will say, okay, this is 140.24.7, which is 8 plus 8 plus 8 is 24, and then dot 26. 26 means it is actually 00. I'm just writing initial 2 bits because everything else can be changed, right? So I'm just writing whatever is fixed. So here it is 140.24.7.64 means I think it is 10, right? I'm just writing whatever is fixed. I'm not writing whatever can be changed. Okay, 140.24.7. This is 26 means I just need 2 bits from here. This is okay. 64 means 01, and this is 01. This is 10. This can be changed. Okay, and then last address is basically this one, which is 140.24.7.64. 192 means 1 1, right? 128 plus 64, 1 1 1. Okay. Now, what does Supernetting says is very simple. Okay. So this is the first time I'm actually telling you the concept of the Supernetting. So Supernetting is basically route aggregation. I want to aggregate these things. So let's just start the topic Supernetting. Okay. Let me know before that if there is any doubt. Cool. What is the Supernetting? It is basically an idea to have the smaller number of entries in the routing table of R2. Right? Now, I just want to have one entry here with respect to this, which is, let's suppose, M0. I just want to know what to write here, right? Default could be anything, however I want to configure it. This is M0. I just want to know what to write here. Okay, let's just start it. See here, see, it is so nice to see that all of these four networks are starting from 140, isn't it? So what will I say? What will this router say? This router R2 is connected to M0, okay, M0, and this is connected to R1, and these are connected to these four organizations, okay. This is organization 1, this is organization 2, this is organization 3, this is organization 4. This is connected to four organizations. Let me know if that is clear. Right? Now this R1 is saying that, see, I am connected to these four organizations, but my interfaces are different. So sorry, I need to have at least 4 entries. I cannot just shorten my entries. So at R1 you cannot do Supernetting. Now at R2 you are saying that, see, I am connected to just M0. So I can say that less like whatever the packet is going to either organization 1, 2 or 3, 4. For me it is just M0. For me it does not matter the 1, 2, 3, 4. So I will say, now just see here, just see this, okay. And one thing I will convey very nicely is this. See, for me these four organizations are actually starting with 140, right? These four organizations are starting with 140. I will have a routing table which will look like this. I will say that, see, the one I can have one of the entry only, and the entry can be, see here very carefully, the entry can be 140 dot, and I do not care. Okay, I will say I do not care. As long as it is starting with 140, I will say let's go to M0. Okay, as long as something is starting with 140 and /8, then I will say go to M0. Is this correct? Is this correct? Let me know. See, with respect to R2, I will say, see, I do not care. If as long as it is starting with 140, because all 140s are here, all 140s are here. So as long as it is any packet which is coming, which is starting with 140, I will ask it to go to M0. Okay, yeah, that is correct, but that's not precise. Let's say a precise number. So I will say that, see, I do not actually care. I do not care as long as something is coming to me which is starting with 140.24, and then I do not care the rest entries. I will say select 16. Okay, so sorry. So I will say that I do not care as long as it is starting from 140.24. Okay, then I will say go to M0. Yeah, this is also correct. I can have this entry. That's fine, because as long as it is starting from 140, I will say go to M0. Maybe I can be more precise. I can be just more precise. I can say, see, not just 140. It should be 140.24. What's wrong in being more precise? Nothing harm, right? So I will say 140.24. Then can I be more precise? Tell me, can I be more precise here? Then I will say, yes, I can be more precise. I will say 140.24.7. I can be more precise. Okay. Now tell me, can I be more precise? Which means I can definitely write 140.24.7. Okay, and then .0/24, right? I can definitely write this. There is no harm in this. But can I be more precise? Let me know. More precise means, can I say that, okay, till as long as it's starting from 140.24.7, I will send it to R1. But can I be more precise? The answer is no. You can be at most this much precise, right? You can be at most this much precise. So this is the answer. Now, okay, don't worry. I mean, we have not completed this Supernetting. I will tell you many interesting things. Now, let's consider a very nice scenario. I don't know if it is nice or not, but let's consider a scenario Here I hope this is done. First let me know if this is done, then I will tell you one interesting scenario where let's suppose that one of the organization, okay, let's suppose the organization number 3 or organization 4 or anything, one of the organization, maybe the organization number 3, okay, the org 3, which is this is the org 3, has been moved physically to some other location. It has been moved physically, okay, it has been moved physically to some other location, which means now let's suppose this is org 3, which is having this address, okay. Suppose physically it has been moved to some other location, which is, let's suppose it is M1. Now let's suppose this is M2. Now tell me, for the routing table of R2, can I have the same thing, which means can I say in the routing table of R2, if something is starting from this, then go to which is 24, go to M0, can I have this entry? See, this will be problematic, right? If something is coming from here and that is meant for M1, let's suppose that is meant for the organization 3, then R2 will say that okay, anything that is start from 140.24.7 and then organization 3 is also starting from same, then it will send it to M0 or maybe R1, right? Okay. So since I can do it, I mean this, if I'm having this entry, then there will be problematic. Then the answer of this question is that yes, you can still do it. I mean there will not be any problem. You can still do it. Okay, even though these are not contiguous. Do you remember the contiguous misconception? I mean this has to be contiguous, right? Even though this 1, 2 and 4 are not contiguous, still you can do the supernetting for 1, 2 and 4, which means you can say that this is 1, 2 and 4, this is 1, this is 1, this is 2, this is organization 4. You can do the supernetting, you can have the entry here just like this in the R2, but you have to have one more entry in R2, okay, you have to have one more entry which is more specific to organization 3. Which entry? You will be saying that see, let's have one more entry where I will say M1, which is 140.24. What is the organization 3? Let me write it here. This is organization 3, which is basically dot these 2 bits are fixed. It means it is yeah. So it is basically 24, 25, 26, right? So dot 7 dot 128. This is 128 dot 128 slash 26. And then M1. How it will work and why it will work? Can anyone tell me? Can anyone tell me that how and why it will work? Do you remember there is one rule called longest prefix match, longest mask match, right? So now this is the correct routing table for R2, even though this 1, 2, 4 are not contiguous, these are not contiguous organization, still I did a supernetting here and this organization 3 is moving here. That's not a problem to me. I can still do the supernetting here, but I will be having one more entry for this organization 3. Okay, so I just need to have one more entry, that's all. And since it is more specific, it is the longer match, then there is a rule called longest mask matching, which means if any IP address that is coming to R2, let's suppose if it is matching to 2 entries, I will forward it to a specific one, which is this one. I will forward to longer mask. If something from this organization must be matching obviously from this entry and this entry, then I will forward to M1 only. I will not forward to M2. Okay, so because of longest mask matching, this supernetting actually works. Okay, because of longest mask matching. I hope this is clear to everyone. See, now are you very clear that it need not to be contiguous? Because even though it is not contiguous, you can still do a supernetting, and because there is a rule that is called longest mask matching, this kind of technique will still work. And these are not my words. See, whenever I encounter any misconception, then we always put a reference that these are, you can find it in the tenant bomb. I must be having the screenshot. Okay, I will paste the screenshot after a break. Okay, so there are like from the tenant bomb, I will paste the screenshots. Don't worry. So these are the common misconceptions that we have, and in the tenant bomb it is clearly written. Actually, this is the example of Trojan. where they have done it, but it is also written in the Tenenbaum, it is also written in many standard books like Frozen. We will have a break after 1 hour, and after a break I will put a screenshot in the meantime of break, okay, here, that are from the books. Let me know if that is clear to everyone. Okay. Now that's how supernetting works. So basically, I hope that you have understood the supernetting concept. So in the supernetting, what you do, you let me just write the supernetting. In nutshell, what you do, we combine couple of networks in routing table if they share same interface. If they are not contiguous, okay. Okay, what is the longest mass matching? See, longest mass matching says, let's consider an example. Let me quickly consider one example. Okay, let's take these IP addresses. Maybe let me just quickly tell you what is longest mask matching. Suppose these are the four organizations which are physically not contiguous. Okay, I mean this is organization 1, this is organization 2, this is organization 3, this is organization 4. Now suppose this organization 1, 2, 4 are connected to one interface, but organization 3 is somewhere else physically. Okay, so which means there is one router R1 which is connected to organization 1, organization 2, and organization 4. Okay, organization 4, this router, obviously this router cannot do supernetting, we can do the supernetting at the router R2, and here I do have organization 3, right? Now let's suppose these interfaces are M0. Okay, now there is, let's suppose, a packet that is coming to the destination address that is coming to R2 that is designed for organization 3. Can you give me any packet name? Maybe it is, if it is starting with 1 and 10, starting with 10, then maybe 130. 130 is starting with 10, definitely, right? So I can say the destination address is, let's suppose, 140.24.7.130. If this is the destination address, if it is coming to R2, then R2 need to decide based on this routing table whether to forward to M0 or to forward to M1. And what is the routing table of R2? R2 routing table looks like this. Okay, R2 routing table looks like this. Okay, let me know if that is clear to everyone. Now, what we will be doing, we will be saying that if that is coming to R2, then R2 will match this destination address with entry 1. Since this destination address is part of this network, it will say that yes, it is matching with 1. So R2 will say that it is matching with 1, then I can forward to M2, M0, sorry. It is also matching with this entry, then I can forward to M1. Since it is matching with two entries, this destination address is matching with two entries. Is this clear to everyone? How it is matching with two entries? Okay, since this destination address is matching with two entries, I will say that I need to forward to the entry which is having the longer or the longest mask, which means this is slash 24 only, this is slash 26. So I will forward it to M1. I will, because it is for M1, and that is done. I mean, that is what we wanted, because this actually belongs to this organization 3. I wanted it to forward to organization 3, right? So it will go to organization 3. Now consider a different scenario where the destination address is actually made for, let's suppose the organization something, right? Maybe let's suppose the organization 2. Organization 2, let's suppose this is 67, because this is 64, this is 64, and then this is, let's suppose, 67. 67 is basically inside this. Now suppose this slash 67 is coming to me. Now what will happen? It will match with only one of the entry. It will not match with the organization 3. It will not match the this entry. It will just match with one of the entry. I will forward it to M0, and that's what we wanted, right? That's what we wanted. So in both of the cases, it will work. Whether it is belonging to organization 3, right? It is not in organization 3, or it is in the organization 3. In organization 3. Whether this IP address is from the organization 3, then also I'm forwarding to organization 3 like this only. If it is not in organization 3, then also I'm forwarding to the corresponding router or corresponding interface, right? In both of the cases, it will work. Let me know if you have understood this clearly. So this is big misconception that this should be contiguous, this should be like this. There is a couple of rules, and actually I don't know that from where they are copying to each other, or like how they, I mean, it must have happened that someone might have derived those rules, and then from 20 years these rules are being copied from one teacher to another teacher. And to my surprise, like, why they cannot even read the textbooks? I mean, why they are copying to each other? Why they cannot just verify the concept from the textbooks? There are many misconceptions that are there in many subjects, right? Okay, so maybe this supernetting is clear to everyone, right? So basically, supernetting is saying that you can combine couple of networks in routing table if they share the same interface. First of all, they must share the same interface. But if you are combining that is not contiguous or something, then I can definitely do it. Actually, I can do anything, because the longest mask will take care of it. Okay, cool. Now let's suppose, okay, now let me go to one example. Now let's suppose that there are some IP addresses that I have. Okay, let's suppose this is R1, this is R2, and this is connected to some organization which is, let's suppose, 131.6.9 anything. Okay, and let's suppose this is basically organization which is 00. I mean, this is slash 26. Okay, 00, and I mean, you do have other bits also, but I'm not writing it. Basically it is 0/26. I hope you are getting right. Basically it is the first subnet that I have generally, so it is 0/26. So this is 00, and let's suppose this is again this is 01. Okay, this is 001, and then let's suppose this is 11, and you are missing one of the entry which is 10. Okay, or maybe let's suppose this is 10, and you are missing the last subnet which is 11. 11 is not here. In fact, 11 is not anywhere in the world, which means 11, this particular IP set of IP addresses which I have, which is basically 131.6.9.11 means 128 plus 64, which is 192, right? So anyway, I write 192/26, but you understood it that it is actually 11, right? So suppose that 11 does not even exist physically in the universe, which means this is .01, this is 131.9.10, and everything is /26/26. Now tell me, can you combine these three networks? For routing table R2, can you combine these three networks? Let me know. If you can combine these three networks, see, these three networks look like this: 131.6.9.0, 131.6.9. I mean, this is 00, this is 01, this is 131. Whatever is the fix I'm writing, whatever is host ID I'm not writing. Okay, .6.6.9 dot 10, and these are changing. Tell me, can you combine these three? See, if you combine these 3, then you will be getting something which is actually 131.6.9, and then you will say that see, like here, since it is not matching, so that's why you will be having slash 24, right? And let's suppose this network does not even exist, which means 1 1 does not even exist in this universe. Okay. Now, if you combine all of this, then you are actually covering some extra IPs, right? You are covering this extra, this network. You are covering this IP, this set of IPs extra. You are covering extra IPs. Okay? You're covering extra IPs. Now tell me, is this feasible to cover extra IPs? Is it good to cover extra IPs? See, what do I mean by that? For the R2, your routing table will look like this now, right? Your R2 routing table for R2 will look like this. If you cover all of this, then it will be looking something like this. It will be 131.6.9.0/24. Let's suppose this is M0. You will say forward it to M0. Is this correct one? Or default will be, let's suppose this is M1. Default is M1. Is this correct, a routing table? Because here you are covering some extra IPs, right? You have actually covered some set of extra IPs which are in this network, which are not actually physically there, right? So you can definitely see, again, this is from the tenant bomb only. You can definitely cover the extra IPs if those extra IPs are not allocated. Okay, these are not allocated, then you can cover allocated. If they are not allocated, you can definitely cover. If they are allocated, then you have one more entry. Okay, and because of the longest mask, see, earlier they were allocated, right? Earlier these are the extra IPs that it is covering, and they are allocated through organization 3. Then you have the entry for the organization 3 also. Okay, if they are allocated, you have that entry. If they are not allocated, you just combine. That's all. Okay, so let's suppose they are not allocated currently. If they are not allocated, you can just combine. There is no problem in this. There is no problem. You can definitely combine. If they are not allocated, if they are allocated, you have that one more entry wherever it is. Okay, see, even though there is a misconception that okay, if it is 3 we cannot combine, there has to be 4 or like that. No, that can be 3 also. You can definitely combine. Okay, and then you will check whether the extra IPs it is covering, those set of IPs are allocated or not allocated. If they are allocated, you write that as a routing table entry. If they are not allocated, you are happy. Okay, later whenever they allocated, you just write it. You getting my point? So this is from the tenant bomb only. Okay, so you can definitely cover the extra page. Why I'm putting so much emphasis on this small topic? Because there has been a latest PYQ that has been asked, and students are having too much of misconceptions in this topic. That's why I have spent so much time. I hope you got it. Let me finally summarize this everything. So basically, let me give one example. Let me ask you. Okay, suppose anything /8, and here maybe let's suppose you are having. Okay, similar one 30, I mean not, let's suppose this is 19.20.0/8. Okay, and anything 17.3 dot or maybe dot 8.3.9/8, something like this. Then just tell me, can you combine these three? Can you combine these three? Answer is yes, because as long I will say that, see, anything that start with 17. Okay, actually these are from the same network only, but yeah, so let me just say um, let's just say this is less 24 less 20. Tell me, can you combine all of this? Can you combine all of this? See, they are not even matching, right? I mean, this is dot 3.4, this is 19.20, this is 8.3. So they are not even matching. But can you combine? That is my question. Let me know. What do you think? The answer is yes. You can actually combine anything. There's not any restriction to combination. Okay. Answer is yes. What is the final entry? You will be writing anything that starts with 17, right? Anything that starts with 17. Backslash 8. There is no restriction to combination. As long as you are saying that, okay, anything that start with 17, if all are sharing the same interface, let's suppose m0, I will say, see, why to have these three entries? Let me just have one entry. Anything that start with 17, I will forward it to m0. That's all. I mean, for me, it's very simple now, right? So you can definitely combine anything. It's not like that okay, this is not matching or whatever. You can just say that whatever is common, write it here, and then you combine it. Place it. Now you will be saying that, see here, the number of hosts that you are having is actually just 2 power 8, right? The number of hosts here is 2 power 8. So total host before combination, total hosts before combining is equal to 2 power 8 plus 2 power 8 plus 2 power 8. And after combining, it's just 3 into 2 power 8, right? And after combining, it is too large. This is 2 power 24. Now the question is, can you do it? Yes. But are you having more host here? Yes, I am having the more host. So you need to check whether the more IPs, the extra IPs, okay, the extra IPs, I will call them extra IPs that you are covering, okay, extra IPs that you are covering, are they allocated or not? If they are allocated, you write that routing entry also. If they are not allocated, you are very happy. Okay, you can definitely combine. Maybe final result is too big. Just in this case, see, final result may be too big than your initial IP addresses, initial set of IP addresses. But let's not worry about it. Okay, you can combine it. Your final result could be too big, but finally whatever you are getting, you just need to check that are you covering extra IPs or not. If you are covering extra IPs, then what do you need to do? You need to just check that the extra IPs that you are covering are allocated or not allocated. If they are not allocated, you are very happy. If they are allocated, have that entry, right? Have that entry, and longest mask which will take care of the things. So as long as things are matching, you just see from the starting. If they are matching, you say that, okay, combine it, right? There is no rule. It is very simplification that I am doing at my end, and there is no rule that I need to follow. I just need to take care of one thing, that am I covering extra IPs or not. If I am covering extra IPs, then I have to be careful. Here in this case, I am covering lot more extra IPs, a huge number of extra IPs. Then I need to check whether those extra IPs are allocated or not allocated. That's the only question I will be asking. If they're not allocated, why to worry, right? Because those IP addresses are not allocated, and no one will forward with that IP address. I can just combine like that, right? Let me know if that is clear to everyone or there is some confusion here. Okay, so that's how the supernetting works. So basically, supernetting is very easy. You just combine if they share same interface. Interface और the router, basically the next hop should be same. Okay, interface से मेरा मतलब है कि next hop. I mean, if they are going to the next hop as same, then you can definitely combine. After combination, check, then check if yes, then actually generally this is not the case, that generally this is not yes. Generally all of them are belonging to the same part of the I mean, geographically they belong to the same part of the region. I hope that is clear to everyone. You just combine if they share the same interface. That's all. That's the only rule you need to follow. Okay, even just forget about the second thing. I mean, generally it doesn't happen. I mean, that IPs are allocated and all. You just combine if they share the same interface. That's all. Now let's do the questions. The routing table of the router is shown below, and then this is destination, subnet mask, and then you need to check the interface, right? Since interfaces are different, now okay, now you cannot do anything. I don't think you can do anything. On which, okay, they are just asking on which router the forward like if the destination address is this, and then destination address is this, then on which interface you will forward. This is not a supernetting question, but can you do the supernetting at this router? Can you do the supernetting at this router? Let me know quickly. Answer is no, right? You cannot do the supernetting at this router. Okay. You can do this question as an homework. I think this is an easy question. So let me move further. These are of the same category. Let me check a supernetting question. Yeah. So this question that has been asking GATE 2022. So let's just do this question because this question is on very much demand. Now this is, first of all, this is little controversial question, and this basically question assumes something. Okay, so let's just do this question and then we will see if this question what are the possibilities in this question. So they are saying that which of the following CIDR notation can be collectively used to correctly aggregate all the subnets in the routing table. So they are saying collectively used, which means this is MSQ first of all. So you need to combine or you need to do the supernetting here such that you are getting not just one entry. They are saying you are getting multiple answers. I mean, you are getting multiple entries. That's fine. I mean, you will be combining such that you are getting multiple entries, and then they are saying which of them are correct. So finally, let's suppose that A and B are correct. So finally, after this, after the supernetting, your routing table will look like this. Okay. Let's suppose if A and B are answers, then after the supernetting, your routing table will look something like this. I mean, you will say that you will be having two numbers A, which means this one 12.20. You will be having these two numbers 12.20.164.0. Subnet mask is 20, and next hop for this is this R1, right? And then similarly you will be having let's suppose A and B are answered, then you will be having 12 dot. Basically whatever is the answer, you will be having that that as an entry, and then you will say that this is the final routing table after the supernetting. So that's the idea, right? So that's the idea. Let's just see this question now. So they are saying that you are getting the multiple entries, and then you need to check that which one is correct. Now see here, the next hop is basically different for everyone. So I mean, the thing is that this should be marks to all because the next hop is different for everyone, and we need to have certain assumptions if we need to consider that okay, this R1 and interface 0 or something is same. Since the next hop is same for everyone, then first of all we cannot do the supernetting. That's why this question is very much eligible for for the marks to all. But let's assume some assumptions that let's suppose this is router R which is connected to R1. Okay, see what are the possibilities here. Let me just tell you. This is the router R where I want to do the supernetting. First thing that we notice is the next hop is different. That's why we cannot even do the supernetting. But since let's suppose if I am allowed to do some assumptions, then let's just check that what are the assumptions that I need to do. This is router R. Then this router R is connected to R1 and it is connected to R2. That is for sure that it is connected to two routers, R1 and R2. Now you just check that these are the two, and R3. Okay, these are the three routers that it is connected to. Now these are the two interface 0 and interface 1. Now see, this is the current topology that I have. Now you do not know where does this interface 0 and interface 1 exist. I mean, you are calling this as 0, this as 1, you do not know, right? You are calling this as 0, this as 1, there is no information here, right? You are calling this as 0, this as 1, there is no information. Maybe it is the case that 0 and 1 are even different. There is no information at all, right? So there are basically, I mean, there are different topologies that can exist. So that's why I am saying that here, I mean, based on the assumptions only I can answer this question. Otherwise, this question is not answerable, right? So if you assume that, let's suppose that this is 0 and this is 1. If you assume that this is interface 0, this is 1. So basically this interface 0 and R1 is same, and I mean the next hop is interface 0 or R1, both are same. Next hop is interface 1 or R2. Interface 1 and R2 are same, right? So then you can combine this entry and this entry, this entry and this entry. So basically then only you can combine. If you assume that this is 0, this is 1, or this is 1, or this is 0, right? Something like this. If you assume something, if you assume that this interface 0 is same as R1 or R2, then only you can combine. You can combine these two entry. If you assume that this is R2, then you can combine these two entry. So you need to assume something. Otherwise, you cannot do this question. Is this clear to everyone? Okay. So here, let's see the possibilities. So basically, these are the 4 networks given to me. So what I did, I just draw those 4 networks in the number line. So these are the 4 networks. I will see that which assumptions are valid here. Okay. So these are the 4 networks that we have. And what I did, I just draw those 4 networks on the number line. Is this clear to everyone? This is the network 1, and network 4 is actually part of network 1. That is okay. This is network 3. This is network 2. Right? Okay. Now let's see the options. See which networks you can combine or which networks you cannot combine. It actually again depends on the next stop. This question is not well framed, to be honest. Okay, but let's see the options. These are the 4 options I have. So let me draw a diagram. So these are the 4 options I have, and then let me just draw a diagram where I will be having the 4 options and the networks all in the same place. Copy these 4 networks. Okay, these are the 4 networks that I have. Now let me do one thing. Let me just draw a diagram where all of these 4 options, and all of these 4 networks, these are the 4 networks that I have. These are the 4 options I have. So I'm not doing anything till now. I'm just drawing it that okay, option A is covering how much range, option B is covering how much range. So basically option A is covering 2 large range, option B is covering option B is I think same as network 1. Okay, option B is and network 1 is same. This is network 1 and this is okay. Yeah, if you apply the subnet mask, then option B and network 1 will be same. So basically like I have written that okay, this is option B, this is option C, this is option D, that option A is covering how much, option B is covering how much, like that, right? Now you want to cover this network 1, network 2, network 3, network 4. Okay, you want to aggregate them. Let's forget about the next hop because that is anyway not same. Okay, let's just see that what is the possibility, and based on that we will have some assumptions. Let's forget about the next hop. Is this okay to everyone? I'm not caring about the next hop for now. Okay, let's see that any combination is possible. I can aggregate anyone to anything. Now can I aggregate this network 3 and network 4, and can I say that option D? See, one possibility is that I cover all of these networks into just one network and I call it option A, because option A is anyway aggregating all of them, right? Option A is anyway covering all of these networks, so why not option A is true? Option A can definitely be true. Okay, is this okay to everyone? Let's just go it step by step. So option A is covering all of the network, so it is in fact aggregating. And what is the problem with option A then? It is just covering the extra IPs. Yes, I know this is covering some extra IPs here, this is covering some extra IPs here, that is fine, but option A is too large, that is covering everything plus some extra IPs. Okay, so since I do not know that, see, I can cover extra IPs only when they are unallocated. If they are allocated, then I have to know that where are those extra IP allocated, and then I need to have some routing entries, right? If they are unallocated, then let's suppose that I mean it is actually this is also some assumption that I need to make, that those extra IPs are allocated and we do not know where are those allocated. Basically, we are not allowed to cover the extra IPs. This is another assumption that I'm making. So the assumption that I'm making is this: we are not allowed to cover extra IPs. Otherwise, option A is true. Right? So actually, this is very ill-framed question, but let's just try solving it because it is very latest question. Now, since option A is covering all of them, but it is covering extra IP, but let's suppose we are not allowed to cover extra IPs. Okay, so that's why option A is wrong. Option C, for the same reason, option C is also wrong because it is also covering some of the extra IPs. I mean, option C cannot be the answer with option C and D cannot be the collectively answer. Although C and D are covering all of the networks, D is not covering anything extra, but C is covering something extra, right? Since C is covering something extra, that's why let's suppose the C and D is also not answer, because let's suppose we are not allowed to cover the extra IP. Then the only option remaining is B and C, B and D. Then B and D is saying the network 1 and network 4 are anyway can be covered, and then network 3 and network 2 can be aggregated. So basically option B and D is the answer. Okay, I'm just ignoring next hop also. See, this question is too much ambiguous. I'm just ignoring next hop also, then I'm able to write it. If I'm not ignoring next hop, then I cannot write it. Okay, so let me know if you are convinced, or there is some issue with this question. Now, if I'm saying that B and D is answer, okay, which means B is saying 1 and 4 can be aggregated and 2 and 3 can be aggregated. 1 and 4, I'm basically aggregating 1 and 4, and which is using B, and 2 and 3 using C. So 2 and 3 if I'm aggregating, it can be aggregated only when the next hop is same. So basically they are assuming that interface 0 and R2 is same. So that assumption has to be made that interface 0 which is this one, and R2 is same. Interface 1 and R1 is same. So basically if they're aggregating these two, then I have to assume that R2 and interface 0 are same. If they are aggregating these two also, R1 and interface 1, then I have to assume that interface 1 and R1 is also same. So basically this assumption about the topology also I have to make. Okay. So Subhadeep is asking that what to do with this kind of ambiguous questions during exam. You cannot do during exam, like you cannot do anything during the exam. Sometimes it is luck. They should mark this to all because they have not specified anything that okay which interface is connected to which router. As I told you that it could be the possibility 1 0 could also be the possibility. How we will get to know, right? In fact, there is a possibility that this is neither 0 or 1, and maybe you have 0 1 extra. Maybe you have this as 0, you have this as 0, this as 1, right? Since it is not given, that's why like you cannot do anything, and during the exam definitely you cannot do anything, unfortunately. So this is 0, this is 1. Based on the answer, I'm trying to figure out that what is the examiner mindset. So obviously if that you have to do, then this is not a good question. Let me know if you have understood. Now, see, these are the different topologies that are possible. Now let's just do few more questions, okay? And let's have the fragmentation questions, and then we will see some of the examples of DVR and all, right? I think after that DVR will be remaining. So actually there is a graph theory also. I don't think we can cover the transport layer today. So let's take a 10 minutes of break. Let's meet at 12:10, and then we will be covering for one more, I think for 1.5 hours more for network layer. And transport layer, if you want computer networks to be covered fully, transport layer we can cover tomorrow morning. Let's meet at 12:10. Hi everyone. Okay, so let's get started. Siddhi is asking, before 2022, you showed one question of CIDR. Okay, um, there, right? Yeah, or in actually in these questions like this question is not route aggregation question, and here, since the interface are different, that's why I was saying that route aggregation is not possible or the supernetting is not possible. So cool. Let's now start a new topic, which is IP fragmentation. Okay, IP fragmentation. So we will be directly solving the questions of IP fragmentation because I assume that this is very popular topic and most of you might already be knowing that how to do the IP fragmentation, right? Okay, let me directly go to the fragmentation question. So let's solve this question. What they're saying, an IP router, which is having it is connected to one network which is having MTU of 1500 bytes. Okay, an IP router with MTU of 1500 bytes has received an IP packet. So this router is connected to some network which is actually having MTU, maximum transmission unit, is 1500 bytes. And what they're saying is that this router is connected like this. Then they're saying received an IP packet of this, and this IP packet that it has just received, it is having 4404 bytes, IP packet of size 4404 bytes with IP header of length 20 bytes. So IP header length is 20 bytes. The values of the relevant feed in the header IP fragmented by router we should be finding. Okay? So let me just go here. So see, you are receiving 4404 bytes. This is IP packet size. But MTU works on the data link layer, which means that it says the maximum transmission unit at data link layer is 1500 bytes, which means in the IP packet size, if it is including the header, okay, then you always have to subtract 20 because it is saying that including the IP, you can transfer 1500 bytes, which means that excluding the IP, you can transfer only 1480. Excluding the IP, you can transfer only 4080. So this is basically excluding the IP. Now this IP packet is also containing the IP header. So that's why you will say the data bytes here. So you need to subtract 20 from both. You need to subtract 20 from MTU. You need to subtract 20 from IP packet. Okay. If it is containing the IP header, I mean the number of bytes are having the IP header. How to check it? It will say IP packet size. Okay, if it is saying the data size, if it is saying data, only the data, okay, then it means that they are only talking about the data, they are not talking about the header. So the data bytes will be 4404 minus 20, which will be 4, and then this will be 834, right? 4384. So basically you have 4384 bytes of data, bytes of data that you need to divide it into multiple parts such that you have each part not containing more than 1480 bytes of data, right? That is your aim. So first check, can you have 1480 here? I mean 1480, this is the first packet. So every packet except the last packet has to be divided by 8. So just check if 1480 is divided by 8. Let me just check. Okay. So 1480, if you divide by 8, I think it is divisible, right? So this is 185. This is very standard number. So this is actually divisible. So if you divide by 8, it will be 185. Now you can divide this into 1480, then 1480, then 1480. I mean, let's just check that 1480 into 3 is what? 1480 into 3, if you do, then you will be getting 4404. So last one will not be 1480. Basically, it will be 1480. I mean, it will not be 1480. It will be something lesser. What it will be? It will be 1480 into 2 into 2. and then that should be like 4384, that should be subtracted from 4384, then you will be getting 1424, you will be getting 1424. Now you do not need to check for the last package. For the last package you do not need to check whether it is divisible by 8 or not. For these two this has to be divisible by 8. So that is the answer, right? I mean, these are the data bytes. The packet size, okay, including the IP header will be, okay, if you include IP header, then it is 1500, it is 1500, it is 1444. If you check other options which are which they have asked more fragment, they have asked datagram length, they have asked the offset, right? Okay, so if you check the more fragment, then it will say yes, there are more fragments, there are more fragments, there are no more fragments. If you check the offset, then you will say it is 185, sorry, it is 0 because it is not following anything. It is following 185, I mean it is following 1480, but 1480 divided by 8, which is 185. It is following 1480 into 2 divided by 8, which is basically 185 into 2, which means this is 370. So what they have asked is basically the values of the relevant field in the header of the third IP fragment. So this is the third IP fragment. So these are the values that they have asked. 370 is the offset, more fragment is 0 and 1444, right? More fragment 0, 1444 and 370. So A should be the answer. Answer is A. There's an easy question. Like you just need to take care of two things. You need to subtract 20 from MTU because this is the IP header length. You need to also subtract which is like 20 from the from the IP datagram size, right? Because you just need to deal with the data. Okay. So Neha is asking, sir, PDU means only payload or some header inclusive in it. So they will specify. If they are saying that this is packet size, then it means that header is included. If they are explicitly saying that this is data size, then it means the header is not included. Okay. Cool. Now, like we will not do much of the questions from fragmentation because all of the questions are of similar type. Okay, if you check any other question, like let's suppose this question is nice question, you just tried it as an homework. This question is also easy question, I mean, and it is of similar type. Okay. Here they just try to confuse you that UDP header is given to you. So if UDP header is given to you, does this matter for the MTU? See, this is the data link layer and it basically says that this is IP, this is TCP, right, or UDP, whatever you have here, and then this is application layer data. Now the IP header size is given, okay. So IP header size is given 20, here it is given 8. Now MTU is given 1500. MTU means this much, right? This much, 1500. This total should be 1500. Now what they are saying? Now they are saying UDP datagram containing 8880 bytes. So basically they are saying 8880 bytes it is containing. Now you need to add this 8 here such that the total data bytes at the IP level it is 8888. Okay, the total size at the IP level is 8888. Now you can do this question in the usual way. Okay, so this is 8888. You need to divide this 8888 into multiple parts such that the M2 is 1500, right? This is the 8888. This is the data part that you need to divide so that each one is having 1480, right? Like that. That's how you can do this question. Maybe if I have done this so far, I can do it like other part also. 8888. Now you need to divide into 1480. So how many parts will be there for the 1480? Can anyone tell me? So this is 8888. We divide by 1480. Then you will be getting 6.005, which means that it is basically 7 parts, right? So this is first fragment, this is the second fragment, and similarly there will be 1 2 3 4 5 6 6 4080. Okay, 4086 times, then something will be remaining, right? Something will be remaining. And what is that is remaining? That is the 7th time. So can you tell me what is remaining here? So you can just tell me by 1480 multiplied by 6, and that should be subtracted from 8888, that is 8 bytes, right? So for the 8 bytes you will be having one more packet. Now how many total packets? 7 packets. And then for the last datagram they are saying, for the last datagram it is the 7th packet, and then it is having 185 into 6. The offset is 185 6. So I think they are asking about the offset, right? So I think C is the answer. Here answer is C. That is also easy question. Using the UDP they try to confuse you, but this is an easy question. Now let's do some of the questions from directly from DVR, right? Distance vector routing. Let me know if I can move to DBR, or you want some clarification or some more questions from this. I think these are the easy questions that you can do. Very easy questions, right? This IP fragmentation is most easiest part in IP. Okay, let's just move to DVR, distance vector routing. And once we finish the DVR and LSR, we will be finishing our network layer entirely, right? There is no single topic that we will be remaining in the network layer. Yes, there are small protocols like ICMP and all. These are error query, and these protocols are there where they, like, you send any router or any host send the ICMP message, is that has to discard the packet. So this ICMP, I think like most of you knows, but if you do not know, then at this point in time that's not a worry, because that's very small topic. Okay, let's just start with DVR. Cool. DVR means distance vector routing. So basically, whenever you have any topology, so every of the router, every of the host has to determine that this should be forwarding packet to which network, or sorry, which host, such that it takes the minimum cost. Which means if this D has to make a decision that if it has to forward to C, then can it forward directly, or should we forward through through E? Basically, it has to find the shortest path from D to everyone else. Similarly, A has to find the shortest path from A to everyone else. Now there are two different protocols to do it. One is DVR, which is distance vector routing. Another one is LSR, which is link state routing. So let's just first see DVR. So what is DVR? It says that you have a couple of router which is arranged in some certain topology. Now you need to determine that this A should be having, like, what is the minimum distance from A to every other node, similarly from B to every other node, similarly from C to every other node. So what it says, it is very easy protocol, or very nice protocol. It says that it initially, whenever the router is connected, it only has the local information. Okay, so initially you only have local information, which means that A knows that it is connected to B, and A knows it is connected to C. So A knows it is connected to B, which means for A, if the like the distance vector for A, it will say that from A to A, if we want to go, it is basically 0. I mean, obviously it is 0. If you want to go from A to B, it is basically 7. If you want to go from A to C, it doesn't know initially. If you want to go from A to D, it doesn't know initially. But if you want to go from A to E, then it knows that you can do it in one. If it doesn't know, then you will keep it infinity. Okay, so only B and E it knows. Obviously A is 0, A to A is 0. So that's called a distance vector that you have at A, right? So that is called distance vector at A. Distance vector at A. Let me know if that is fine to everyone. Now at B, similarly you will be having one distance vector. At E, similarly you will be having some distance vector. So let's just see the distance vectors that we have at B, C, D and E. And once you have those distance vector, this is just an initialization. So this is initial part I'm talking about. Then you need to send those distance vector to the neighbors. Okay. So maybe I can take another example, because I have that in my slide. So what will happen, that you will be having some distance vectors. So this is, let's suppose this is the topology I have. Okay. Don't worry, I have multiple examples, so we will be covering it fully. So we will be solving the gate pivot as usual. So for now, let me just start with one of the textbook example. So suppose this is the topology that I have. Now what will be having initially, initially I knows about J and E only, about the neighbors only, right? And then what will happen, then this I will be having one distance vector. It will forward its distance vector to every of its neighbors. So let's suppose that I'm talking about J. Okay, at J, since it is having 4 neighbors, it will be getting the distance vectors from 4 nodes, right? So if J is having the four neighbors, then J will be getting distance vectors from 4 nodes, which is A, I, K and H. So J will be getting distance vectors from A, I, K and H. So these are the 4 distance vectors that I have. Now, based on these 4 distance vectors, I need to compute the new distance vector for J. Okay, so that's the idea. How we do it? Let me just show you using an example. So let's take this example, or maybe let me take one example, which is this one. So let's just say this is A, B, C, D. Let's just say it is A, it is B, it is C, it is D, right? Now what will happen? Initially, you will be having some distance vectors. Can you write those distance vectors? So let me quickly write. For A, it knows about B, it knows about C, and it also knows about D. Okay. So it knows about all of this. A knows about B, C, and D. Direct distance is known, but it need not to be shortest, right? I mean, just look at this A. Now at 3 you can read directly to D, but this is shortest. This 2 is shortest, right? So direct distance is known, but it doesn't mean that it is shortest. Okay. So from A to A, it is 0 definitely. And then from A to B, from A to C, and then from A to D. So you know these 4 distances, which are A to B is 1, and then C is 7, and then D is 3, right? So you know this 0, 1, 7, 3. Now for B, you know that okay, B to B is definitely 0, and then let me do one thing. Let me draw a vector that I will be copying again and again, which is having the 4 slots. Copy this. Just a second. So let me write it here. So now let me fill those entries that you have for the ABCD. So this is just an initialization, right? For the initial purpose, you will be having some entries in ABCD. So here, this is 0. Here, this D to D is 0. Here, the C to C is 0. Now you write the remaining entries. This is B to A is 1. B to C it doesn't know, but B to D it knows, which is 1. And this is infinity. If it doesn't know, it is infinity. Now D to B it knows. So this is A, B, C, D. So D to A it knows, which is 3. D to B it knows it is 1. C it is 2. Again, it is A, B, C, D. Now C to A is 7. C to B. C to B it doesn't know. C to C is 0. C to D is 2. Right? So these are the initialization. Initial distance vectors. Initial distance. Let me know if that is fine to everyone. Okay. So if that is fine, let's just move further. Now what we will be doing, now this A will forward its distance vector to B, to D, to C. Similarly, C will forward its distance vector to its neighbors. Now let's just see that what is happening at A. A will be receiving from 3 nodes, C will be receiving from 2 nodes, similarly B will be receiving from 2 nodes, and so on, right? So at A, what do you have? Let's just see. So these are the initial vectors that you have. Now at A you will be receiving 3 vectors. At A you will be receiving vectors from B, vectors from C, from B, from C, and from D. You will be receiving 3 vectors. Let me write all of those 3 vectors from B, C, and so you will be receiving 3 vectors, which is from B, from D. Now this is called iteration. This is called first iteration. See, initialization is not called any iteration, but now in the first iteration, A will be receiving the vectors from all of this, B will be receiving vectors from all of this, like that, right? So now let's just quickly do it. So A will be receiving vectors from B, and B vector is 1, 0, infinity 1. C vector is 7, infinity 0, 2. D vector is 3, 1, 2, 0, right? Let me know if that is fine. Okay. Now, if this is fine, let's just move further. Now, based on this, A will be recomputing its own vector, which means A will say, okay, so A has to recompute its own vector, which means earlier, whatever it is, let's not worry about it. Okay. So earlier, like, I mean, see, conceptually also, like you are getting from B, C, D, I mean, you are getting all of the vectors from the neighbors. So earlier what you had, like you should not care about it, because there is the latest information that I am having from my neighbors, right? Whatever I had earlier I should not be worrying about it. So first of all, you need to check the distance from A to B itself is 1. Distance from A to C itself is 7. Distance from A to D is 3. So basically this is the vector from B, which means B is saying that I can reach to, this is A, B, C, D, I can reach to A. Okay, you don't need A first of all, you will be writing, for A you will be writing it as 0. For A you will be saying this is 0, and then you need from you need to go to B, you need to go to definitely C, you need to go to D, right? You need to go to all of this. Now you will say that okay, if you want to go to B, then this is basically 0 plus 1. Always add this number because at least you will be incurring the cost of 1. This is saying 1, this is saying that it doesn't know, and this is saying 4. So you will say that okay, if you want to go to B, then you should be going in 4, or you should be going in you should be going in 1, because this is giving you 4 and this is giving you 1. So that's why you should be going in 1. Let me know if that is clear to everyone. Let's just do step by step. Okay, so that's called distance vector routing. So how I am doing it? First is initialization, and then at A I will be getting 3 vectors. I wrote those 3 vectors. Then this is the cost from A to B, right? This is the cost from A to C. This is the cost from A to D. I need to add this cost basically. This is 1 plus 1, 2 like that. And first I need to fill this 0, and then I will fill in the remaining entry. Here it is infinity. Here it is 7 plus 0, 7. Here it is 2 plus 3, 5. So I will write in 5. Earlier it was 7. Now it got 5. That's fine. Now it is 2. It is 9. It is 3. 2, 9, 3. So which one is smaller? 2. So I will write in 2. Earlier it was 3, but now it is 2. It is better. So anyway, like from earlier I should not even compare. Okay, there is no merit of comparing with the earlier. There is no point in comparing with the earlier. Only I need to compare among this. Reason being is that earlier is absolute, right? I just have the latest information with me. Now a new vector is this one, right? This is the a new vector. Let me know if that is fine to everyone. Now similarly at B, okay, at B what you will be getting, let's just check. So at B you will be getting 2 vectors, okay? You will be getting vectors from, one is from A, one is from D. One is from A, one is from D. Now what are those vectors? Are you getting the latest vector which is 0, 1, 5, 2, or you will be getting this old vector only at B? Okay, you will be getting this 0, 1, 5, 2 or the old vector which is 0, 1, 7, 3. So let me know. Let me know if you will be getting the old vector or you will be getting the new vector. This is something important that I want to ask, because I want to do this algorithm little slowly so that you understand each and every iteration. Otherwise there is no point in even doing this algorithm, because if you miss something, then you might not be able to do the question in the exam. Okay, so see here, generally what happens that A and B both simultaneously send their vectors. Even there was one recent question in GATE 2022, they have asked about it only, that if they do not simultaneously send, and then what is the count to infinity and all. So they have asked something like that. So we will check it, but for now let's understand it, that if like generally what happens that A and B simultaneously send their vectors to each other. So it is the old vector only that we will be dealing with. We will never deal with the new vector in the same iteration. We are at iteration 1. Okay, this is the first iteration only. This is the first iteration only. Okay, we are not even at the second iteration. Now we will be getting the old vectors, which means I will be getting vector from A which is 0, 1, 7, 3 only. 0, 1, 7, 3. I will be getting vector from D which is 3, 1, 0, 2. 3, 1, 2, 0, sorry. Yes, Lalit, that is right. We will be getting the old vector. Now you need to compute the vector for B. So let's just compute the vector for B. So since you're computing vector for B, that's why you will be writing 0 here, because B to B is anyway 0, A, B, C, D. And then if you want to go to A, right, then it is saying, let's just write the cost maybe here. A B cost is 1, and to D it is 1. Okay. So it is saying you can go to 1, you can go to 4, so obviously 1. You can go to, okay, this B is anyway 0. You can go to 8 and 3, so obviously 3. You can go to 4 and 1, obviously 1. So 1, 0, 3, 1, that's the new vector that you got. Now, although it is a new vector and I should not be comparing with the old vector, but just for the sake of human nature, I just want to check that I have something changed. Yes, it is 1, 0, infinity 1, 1, 0, 3, 1. Okay, at the C I have improved a little. Okay, cool. I hope that is fine. Now let's check what is happening at C, right? At C what is happening? See, at C, let's just check. At C, you will be getting two vectors, one from A, one from D. So you will be getting two vectors, one from A, one from E. Now it is just iteration one only. Everything is just iteration one. It is just iteration one only. Now you will be getting one vector from A, one vector from D. So the vector that you are getting from A is basically just old one. From D, you will be getting 3120. 3120. Now let's just write, okay, let's just write this vector, the new vector for C, where it will be 0, and then A to C is 7, this is 2. 7 plus 0, 7, and this is 7. You can write any 7, I mean next hop could be anything. This is 7 plus 1, 8, this is 3, you write 3. This is 7 plus 3, 10, this is 2, you write 2. So 7320 is new vector. Earlier 7 infinity, sorry, 7302. So 7 infinity 02. So from infinity you improve. But anyway, like I should not be even checking with the old vector. Is this fine? This is just iteration 1. Now at D, similarly, at D you will be getting some other vectors which are three vectors you will be getting. Okay, from A you will be getting, from B you will be getting, from C you will be getting. From A you will be getting just the old vectors only, 0 1 7 3. From B you will be getting 1 0 infinity 1. From C you will be getting 7 infinity 0 2. So this is again just an iteration 1. You need to understand this iteration by iteration, because in the gate they have asked question iteration by iteration. Okay, so let's just understand this using the iterations. Now let's just compute the final vector for D. Okay, the final vector for D. This is the final vector that I want to compute. Now distances from A to D is 3. D to B is 1, and C to D is 2. So D to D is 0, so that's why I'm writing 0. It is saying 3 plus 2 plus 9. So 2 is minimum. It is saying 4 plus 1 plus infinity. So 4 plus 4 and 1. So 1 is minimum. It is saying 10, infinity, and 2. So 2 is minimum. So 2, 1, 2, 0. Okay, this is the vector that we are getting at D. Let me know if that is fine. So now we have new set of vectors at A, B, C, D. This is the iteration 1 completion. Okay, I just completed the iteration 1. Let me know if that is fine. So now let me write the new vectors at A, B, C, D, because I just completed the iteration 1. So after completion of iteration 1, I will be having something like this. So this is basically after first iteration completion. I mean, this is not here. So let me just copy the vectors that I'm getting. At A, I got this, which is uh, this one, 0 1 5 2. So yeah, actually this is little lengthy process, but we have to do it because the questions that they ask iteration by iteration. Okay, so this is 0 1 5 2. At B, I'm getting 1 0 3 1. This is 1 0 3 1. Right. At C, what I'm getting is, let's just see at the C. So at C we are getting 7302. See, if you understand this algorithm step by step, then only you can solve the question, and there will be a 2-mark question if at all there is, right? So C we are getting this, and finally at D we are getting this one, 2120. So these are the vectors that we are getting, and this is after completing the first iteration. Now let's just see that what's going to happen in the next iteration, right? So this is after completing the first iteration only. Now let me know if there is any doubt till this point. I hope you understood. Now let's see that's what's going to happen if you are going to have the next iteration. In the next iteration, what will happen? At A, you will be getting three vectors which are from B, C, D, right? Let's just first check whether you will be optimizing something or not. See, to C, the minimum distance is 4 actually, right? 1, 1, and 2, 2, and this is 4. So probably this will get increased. I don't know, but let's just see, right? Do you even know that it will get increased? Do you know that this will get increased or it will not change in the, it will get increased now or it will get increased later? Can you tell me? See, A to B is fine, A to C is not fine, A to D is 2, which is fine. So this is not fine here. Similarly, B to A is fine, this is fine, this is 3, B to C is 3. Is this fine? Yeah, I think this is fine. B to D is 1. So this is, everything is fine here. From C, this is 7, this is 3, which means C to B. C to B is 3, I think this is fine. And then C to D is 2. So I think this is also fine. This is 2, yeah, that is fine. This is 1, which is to B, that is fine. To C, this is fine. To D, this is fine, right? Only entry which is not fine is this one. So anyway, like, can you tell me that will this entry be updated in the next iteration or next iteration? Is there any way or any theorem using which we can tell? Yes, there is a theorem or there is a way which we will actually study tomorrow, because that's the part of algorithm that is called Bellman-Ford algorithm, right? Bellman-Ford algorithm. You will be amazed by seeing that how does the Bellman-Ford algorithm work. You might be knowing that we need to run it n minus 1 times and it works. It works somehow, right? Somehow. You might be knowing it, but why? Why? How many of you can tell that why it works the way it works? If you can answer this question, then you can answer this question also, which means that will this get be updated in the next entry or not. So actually tomorrow we will be talking about the proofs of some algorithm, which is Dijkstra, Bellman-Ford, which are actually needed, right? Which are needed for gate. You will be not just by hearting that okay, this is how it works. You will be getting to know that why it is working the way it is working. If here do you, like here do I have any Go classes student who is currently watching this this particular session? Then you, if you have watched, then please let me know that that do like I mean have I was I able to convince you in the lectures that yes, Bellman-Ford is working in the way it is working. Okay, the way it is working, like why it is working in the way it is working. Okay, so see this A to C minimum distance, if you just check, it is 1 2 3 3 distances away, right? I mean 3 edges away. If it is 3 edges away, then after 2 iteration, I mean in the 2 iteration, you will definitely be updating it. Okay, so anyway, at A, let's just check what you are getting. So at A, you will be getting, let me write it here. At A, you will be getting 1031. From B, you will be getting, from C, you will be getting, from D, you will be getting, right? So let me write the entries that you will be getting. Okay, so you are getting. So someone is asking, can we not use the float reversal or something? See, it is not your choice. This is the how the algorithm works. DVR is using Bellman-Ford, right? I mean, it's not your choice. It's how this algorithm work, and this is same as that we have here in the Bellman-Ford. Okay, so now let's just check what I will be getting. 1031, and then C is having 7301, 7302. This is 2120, and then finally I will be getting some vector which is basically here. Now A to B is 1, A to C is 7, and then A to D is 3. So this is 0 anyway. Now let's just write other numbers. This is 1, 10, and 4, right? So this is 1, and then 4, 7, and then 5. So this is 4, right? See, this has improved, and then 2, 9, and 3. Then obviously 2. See, this has improved from 5 to 4. Now I am not doing any like I'm not doing the second iteration completely, although they like B will be receiving the vector, C will be receiving the vector, and D will also be receiving the vector. But since I know it is already perfect, then I know it is not going to change because it is already shortest. Okay, so that's why I'm not doing it. So finally you will be having 4 here, and then everything else will be same. So the final that you are having after the second iteration is this. Okay, that's the only change that you are having after the second, even after the second iteration. So let me write it here that after the second iteration you will be having. So that's how DVR works. Let me know if you have understood this completely. So you need to do it iteration by iteration. Okay, initially, what is the initialization? Let me just tell you. See, this is the initialization where it knows only about the neighbors, right? This is the initial distance vectors where you only knows about the neighbors. Now you need to start the iteration 1 where the exchanges happens, right? And it will be getting the old vectors only. This is iteration 1, this is completely iteration 1, and then after first iteration you will be getting this, right? And then this is okay, this is after first iteration, and then this is the iteration 2 basically, right? So now this is the iteration 2, and if you run this iteration 2 completely, you will be getting this after the iteration. Okay, thank you, Avirya Jyoti. So Avirya Jyoti is saying, "Hi Sachin sir, I have been watching yesterday lectures and I can't stress how helpful and videos are. All of the concepts have been brushed up and just in few hours. Thank you so much, sir. You are most welcome." So just I will just say, just put that same comment there, okay? Same comment in the video, so that it will be visible to others. Okay, so Deepak is asking one doubt. Deepak, that we have cleared yesterday. Okay, he's asking whether we should be using 1 plus 2a or 2a. So we have cleared it yesterday only, right? You just watch that data link layer lecture. Cool. So that's how the DVR works. Now there is a problem in the DVR that is called count to infinity. Okay, let's just quickly see the count to infinity problem, which says that good news decrease, good news travel fast and bad news travel slow. So it says that good news, what is good news? I will just tell you. Good news travel fast and bad news travel slow. Now you might be thinking that it is good thing, right? I mean, why it is a problem? It is good thing that if good news is traveling fast and bad news is traveling slow, why it is a problem? It is even a good thing. No, I want both of the news to travel fast. Okay, we want both of the news to travel fast. Both of the news to travel fast. And based on this count to infinity, there has been just one question, one or two questions that has been asked. So Siddhi is asking how in the second iteration is C part of A is 4. Okay, in the second iteration, why this is 4? Because this is 3 plus 1, which is 4, and the 4 is minimum. That's why I am taking this as 4. Right? This is 2 plus 3, which is 5, and 5 is not minimum, and 4 is minimum. That's why I'm taking it 4. Now, what is a good news? Good news is decrease in cost, okay, and bad news is increase in cost. If it is increase in cost, it travels slow, and that's not what I want. You may say that, see, it is bad news, then and it is traveling slow, then it is fine, right? They are not humans. They need to be very updated. Whatever news it is, it should be traveling fast, and that's the problem that we call count to infinity. Let's just see this problem, and let's just see that how what this problem is saying basically. Okay, so here I have the diagram. Now let's suppose, okay, let me first tell you for the case 1 where I do have a good news, which means that decrease in cost. So let's just see a case where I have the good news. Good news. Good news means decrease in cost. Now just see here, see, this is B and C. Initially, let me just write the distance to A only, okay? Distance to A only I am writing. So distance to A, initially it is infinity, it is also infinity. This is initial. I am only writing distance to A. There must be distance to B, distance to C, but I am only writing distance to A. Okay. Now let's just see the other things. Now let's just see that if you're writing distance to A, then let's suppose that after some time this particular link get connected, which means you are having this, and this becomes a good news, which means that the links are getting connected and the decrease in cost is happening, because the earlier cost was infinity, but immediately once you connected, okay, then the immediately B will update it to 1, because let's suppose this is just one cost and this is also one cost. B will update it to 1. C still doesn't know. C will say it is infinity, right? Okay, let me know if that is clear to everyone. And till now there is no iteration. See, if we are connecting or disconnecting something, then this is not called iteration. If we are exchanging the distance vector, that is called iteration. So that's just in the, I mean, spontaneous. Okay, instantly you will be doing it. Now there will be exchanges. Okay. Now I'm talking in terms of exchanges. Let's suppose, see, there has been a gate question, very recent gate question on this problem also. Let's suppose I'm saying that C, okay, this B is transferring its distance vector first to C. If B is transferring its distance vector first to C, right? I mean, okay. So here at C, you will be getting distance vectors from B. At B, you will be getting distance vectors from A and C, from A you will be getting from B. But let's worry about only B and C. Is this fine? Initially, whatever was set up, right? I hope that is okay. And then once you connect both, then instantaneously that's happening. I mean, without any exchange. Okay, instantaneously that is 1 and that is infinity. Now let's just see the exchanges now, which means C will be getting vectors from B, B will be getting vectors from A and C, right? And I'm writing distances to A only. These are the distances to A. Okay. Now see, B will be always be getting distance to A as 1 from A, so B will never change from this 1 to anything else, right? It will always be 1. Now C will be getting distance from B, which is 1. Now C will immediately say that after just one exchange, it will say it is 2, right? After just one exchange, it will say it is 2. See, at C you will be getting only one vector from B, right? So you will be updating it to 2 because B is saying 1. At B, you will be getting two vectors. One is from C, another one is from A. Then you always be preferring A because that is telling you the least cost. So that's why it is 1. So just after one exchange, that is the situation. After one exchange. Just after one exchange, this is the situation. Which means if it is good news, which means just a connection, then just after one iteration, you are getting the good news to be traveled. If it is a bigger network, then maybe 2-3 iterations. Okay, I'm not saying always one iteration. If it is bigger network, maybe 2-3 iterations. But if it is very small network, then in this particular case, just after one exchange, we are getting our answer. So are you all convinced that good news, which is decreasing cost, which is basically infinity to 1, which is decreasing cost, right? Good news is traveling fast, right? Good news is really traveling fast. Now let's just see if bad news is also traveling fast or it is traveling slow. If it is traveling slow, then it is a problem. Problem does not mean that it is wrong. It is just mean that I need to wait for some time. That's all. Okay. So let me first talk about the bad news maybe. See, just after one exchange, I mean, you will be having 1, 2 here, and it will not get updated after it, right? It is just 1, 2. Okay. Now let's just have a bad news. Bad news means that you are basically disconnecting something. Suppose that this is your initial setup. This is initially you are having this as 1 and this is, I'm just writing a distance to A. This is 2 and then this is obviously 0, but I'm not writing it. But let's suppose something happens and this is getting disconnected, which means this is a bad news. The link is getting broken. Okay. The moment the link get broke, then immediately it will update to infinity. It is still 2. Till now there is no exchange. Now the exchange begins. Okay. After it, the exchange begins. See, whenever you are disconnecting, there has been a gate question also. That's why I'm repeating again and again. Whenever you are disconnecting or whenever you are connecting, that's not called exchange. Okay, that's not called exchange. That happens spontaneously, which means, see, earlier also we were just connecting it. Immediately it will be 1. The moment it get disconnected, immediately it will be infinity. Okay. So I hope that is fine. Now in this situation, what will happen? B will be getting distance from C, which is 2, right? So B will say that, okay, let's suppose, see, in the exchange there are two cases. One is that B sends its vector first to C. Another one is the case that C sends its vector to B. Let's see two cases. Okay, so here there are two cases that B sends its vector first to C, and another case is that where C sends its vector first to B. Are you all convinced with this? Okay, learn with me saying that please clear once again why for C it is 2. Which one? This one. Because C is getting vector from B And since it is 1, it is getting a vector from B. Only from B it will be getting. B is advertising it 1 and B2C itself is 1. Then it will be 1 plus 1, which is 2. Right? Okay. So I hope that is fine. I mean, initially it is the case. Once you disconnect, it is infinity, it is 2. Now just listen carefully. Suppose that C is sending vector to B first. There are two cases now. Okay. So maybe I can go to the next page. Let me write here. There are two cases. B sends, or maybe like as a case one I'm saying, C sends its vector B first. Second case is that B sends its vector to C first. B sends its vector to, okay. These are the two cases. So Sukesh is saying that why would there be two cases if vector exchange happens simultaneously? Yes, this is also another case. Okay. So there are, I mean, there are actually the three cases, but I mean, if vector happens simultaneously, then also it will be covered in one of the case. Okay, don't worry. So let's just see this and then you will get to understand. Yes, generally vector happens simultaneously. Yeah, I completely agree to your statement. But what if that it doesn't happen simultaneously? If it is happening simultaneously, then it is actually covering, I mean, these two cases actually covering the possibility. I will tell you how. But what if that is not happening simultaneously? Okay. Suppose that I mean, C is advertising that to, I mean, to B, which is saying it is 2. Okay. So let's just see. Let's just see what will happen. If it is, even if it is simultaneous, does not matter. So let's just see the case one. Now, this is the case where I'm saying C is first advertising. So if C is advertising first, okay, I'm in the case one, let's suppose, where the C is advertising first. Case one. Now, what will happen in this case? In this case, you will say if C is advertising first, then this from B you will be getting only from C. Since it is 2, so B will update it to 3 and C will be just 2 only because C have not got any vector yet. Right? So this is after C advertised to B. Now let's suppose now this vector got updated to 3 and now this is getting advertised to B. So what will happen if 3 get advertised to this 3 get advertised to C, this will be saying that okay, now it is 4 and now suppose this 2 is again getting advertised, or maybe like it does not matter, maybe let's suppose that I mean the updated 4 will get advertised, or maybe let's suppose that that is happening simultaneously, then which means this 3 is going here and 2 is going here. If 3 is going here, it will be 4. If 2 is going here, it will be then 3. Then again 4 will go here, 3 will go here. So 4 will go here, it means it will update to 5 because that's the only option it has. 3 will go here, it will be just 4. Then again, I mean, it depends. Let's suppose it is happening simultaneously. Okay. Only at the first case, I'm taking that it is not happening simultaneously. Even if it had simultaneously, it does not matter. Okay. I mean, I will tell you that what will happen in case of simultaneous. So basically, it will keep on incrementing. If 4 is going here, it is 5. 5 is going here, it is 6. So it is keep on incrementing. After some time, it will be, let's suppose 20, 20 or 15, 15, something like this. After some time, it will reach to the maximum value, and let's suppose 15 is the maximum value I'm saying, which means that after some time I will get to know that these are infinity, right? After some time I will get to know that these are infinity. So what's going to happen, that I will get to know that this is bad news, but after some time, right? It takes a long to know that it was a bad news, right? It takes a long to know that it was a bad news, which means many iterations it took to just get to know that okay, it was a bad news. Is this a wrong thing? Is this wrong? Let me know. Is this wrong? Is there something wrong with the algorithm? No, there is nothing wrong with the algorithm. It is just slow. Okay, this is not wrong. So basically, you will say count to infinity. Count to infinity. This is not wrong. It is just slow. This is just slow. Count to infinity is not wrong. It is just slow. Is this okay to everyone? because I'm getting to know this bad news very late. Now let's see the case where I'm getting the vector simultaneously or maybe anything. I mean, it does not matter actually even if it is simultaneously. So let me just tell you what, I mean, it will not matter, but let's see the case where let's see the case that B is sending first. Okay, suppose B is sending first. I will tell you the simultaneous case also, and C is not sending yet. If B is sending first and C is not sending yet, then it means if B is sending, then this will be infinity obviously, and then this infinity will be received to C, and then since it has only one option, then immediately it will be infinity, right? If B sends first, then this there will not be any counter infinity problem. If B sends first, then there, let me know if this is okay to everyone. Which means if this infinity is it is advertising, and then 2 is not getting advertised here, then there will be no counter infinity. So learn with me saying if it is not wrong, then why it is called problem? It is just a name. I mean, problem does not mean wrong. Problem means it is a problem with the algorithm. What is the problem? It is very slow. So I can also say that there is some problem with the algorithm. What is the problem? Is time complexity is very high. I mean, it is very slow algorithm. That's the problem with the algorithm. Problem does not mean it's the wrong thing. It just means it could be something else also, right? It is not something wrong. It is just slow. That's all. I mean, the network will not converge very fast. Very lately it might get to know that okay, there is a problem, that's why like I mean, I might have to suffer a lot, right? Okay, so if B sends first, then there will not be any problem of count to infinity. Now what if both are sending simultaneously? Then also there will be a problem of count to infinity, which means suppose if both are sending simultaneously, then what will happen? This 2 will get delivered here, infinity will get delivered here. Since 2 is getting delivered here, it will be updated to 3, infinity getting delivered here, it will update to infinity, because that's the only option that I have. Then again, infinity is getting delivered here, 3 is getting delivered here. So since infinity is getting delivered here, it will be infinity, it will be 4. Then again, 4 is getting delivered here, it will be 5. Infinity is getting delivered here, it is infinity, right? Then it will be infinity, it is 6, like that. So after a long, you will get to know that both are actually infinity. So it means that bad news travel slow. It is also a problem of count to infinity. Okay. Now, now let's just see that how to solve this problem. Okay. Then we will see the gate PYQs. So the solution is very simple. We say that do not use the value which I know from you, which means if you are having, let's suppose if whenever this B is advertising, okay, to infinity, or maybe C is advertising to B, since this value is known from B, then C will say that if you want to know the path to A, then C will say that I know, but that is from you only. So C will say that I don't know. I mean, I whatever I know is it is from you. So I will not tell you that path, because there is no point in telling that what I know from you. If next hope is just you, I will not advertise it, right? Okay, so C should not advertise to B, because next hope is B. C should not advertise to B, because let me just write in simple terms, next hope is B. Okay, so don't worry, we will be covering the gate PYQs. From that you will get to know. Okay, so this is very simple solution, but this solution does not work. Okay, this solution is called split horizon anyway, but the name is not important. But this solution does not work in the bigger networks. This may work in just two 3 nodes or 5 nodes, but in the bigger networks, if there is bigger loops, then it does not work. Okay, so whatever the solution that we have just seen, it does not work in bigger networks. Whatever the solution that we are currently suggesting. So what works in bigger network is actually not in the GATE syllabus. That is called, instead of distance vector, that is called path vector. Okay, path vector routing is basically like it works in all the cases, but that is not in the GATE syllabus. So we should know what is the count to infinity, whether it will work or not, that also we should know, right? So it does not work in all the cases, which means in bigger networks it may not work. Whatever I just suggested you as a solution does not work. Okay. So Sukesh is saying, does this mean that current node will send the distance of infinity to all the neighbors? Yeah, it is sending to all the neighbors. I'm not getting. So only the neighbor here is C, right? So it is sending to C. So basically, if it is C will not send to C will not send this 2 to B, because this 2 is from B only, right? Because this 2 is learned from B. So if you're learning from the same node, then you should not advertise that to same node. It is like कि मतलब हाँ मुझे मत सिखा, like you got to know from me only, then you should not tell me okay what to do, what not to do. Cool. Now let's see some question, which is a very nice question that has been asked in GATE 2011, and there has been two questions that they've asked, and this question should clarify what is this. I mean, how these iterations are working. Then we will see some question related to count to infinity. Then that will clarify that how does the count to infinity work. Okay, cool. So let's see this question. Since this has two parts, I have written that in the next slide. This is the one part. This is GATE 2011 question. So this is GATE 2011. Let's see this question very carefully, what they are saying. Consider a network with 5 nodes, which is n1 to n5. Okay, and as shown below, the network uses the distance vector routing. Once the routes have been stabilized, the distance vector are as follows, right? So which means they are saying that this is the fixed distance vector once everything is finalized. So they have helped you actually. Otherwise, you have to find the shortest distance. But anyway, each distance vector is the distance of best known path at that instant to all the nodes. So n1 to n5, where the distance to itself is 0. Also, all links are symmetric and the cost is identical in both the direction. This is just a general information, that is okay. Now let's see the information which is important to us. See that how they have defined the round. In each round, all nodes exchange their distance vector with respective neighbors. Is this clear to everyone? What is a round here? In each round, what's going to happen? All nodes are going to exchange their information to the neighbors. That's what we have studied, right? Then all the nodes update their distance vectors. Okay. Now see this point also. In between two rounds, if there is any change in the cost of a link, that will cause to incident node, that will cause to change in the incident nodes, that will cause the two incident nodes to change only that entry in their distance vectors, which means that if we are exchanging something, that is called round. But let's suppose if this 6 is getting changed to 5 or something, then immediately that n2 entry will get changed for n3. For n3 you will say that this is 5, okay, to n3 this is 5, something like this, and then from n3 to n2 it will also change 5, but it is not considered as round. That's what they are saying. If you are changing some cost in between, then this is not a round, this is in between round. Okay, that's important that they are calling it in between two rounds. Any change of the cost of a link will cause the two incident nodes to change only that entry in their distance vector. So Sumant is saying, sir, please, once what are all the cases? We should not consider them as iterations. No, you should consider everything as iteration. Whenever you are exchanging something, you should consider that as an iteration. If some link cost is getting changed, then that particular entry, let's suppose n1 entry in the n2 routing table, okay, that immediately has to be changed. That's not a round. That's all. Okay, that's not a round. That's what we are saying again and again. So that's happened in between two rounds. See here, earlier I told you that I think, yeah, this here, if I'm reducing this, or if I'm breaking this link, or I'm joining these two A and B, then this is immediate, spontaneous. You are doing it. This is not a round. The round happens after it. Okay, have you understood this? See, earlier also, if you are joining them, then this is not a round. Immediately it will be one. Then there will be a round after it. After this only there will be a round. If there is a cost change in cost, then this is not a round. Okay, that's what they are saying. If there is change in cost, then this is not a round. Okay, now let's just continue. Now what they are saying? They are saying that what they are asking, the cost of link N2 to N3, is this visible to everyone? Okay. The cost of link N2 to N3 reduces to 2 in both the directions. Now they are saying that see, so they are saying this cost of link N2 to N3 is reduces to in both the directions to 2. It is getting changed to 2. Then after the next round of updates, so this is not a round. First of all, this is not a round. So whatever routing table I have at N2, that will change its entry to N3, N1, N2 and N3 to 2. And similarly, this is N4, N5, right? Similarly, N3 will also be changing the entry to N2 to S2, which means N3 will be saying this is N1, this is N2, which is 2, and remaining is other. So this is not the round. That's what I'm saying. Okay, this update is not a round. Now you will be having a round. They are saying that after this round, what are these values? Right? This very easy question. Now let me just copy these vectors. These vectors, let me copy. Now this is the initial vectors that we have. Not the initial vectors. I mean these are the after the some. After the some establishment has been happened. These are the vectors. Now you are saying this has been changed to 2, which means N2 will change the N3 to 2, and 3 will also change this to 2, right? So that's what will happen. Now they are saying what will the new distance vector at N3? So at N3 you will be getting from N2 and N4. Very easy. From N2 you will be getting, so from N2 and N4 you will be getting, so you will be getting 10273, that is from N2. From N4 you will be getting 87204, that is what you will be getting. That is all. And then you can write the cost of N2 to N3, N2 to N3, sorry, from at N2 they're saying, or N3, okay, they're asking at N3. Yeah, so N2 to N3 is 2, and here it is also 2. Now let's just write the cost. So this is basically N3, which is N1, N2, N3, 0, N4, and N5. So this is 1 plus 2, 3, it is minimum. 0 plus 2, 2, it is minimum. And then this is 0. And then 7 plus 2, 9. And then this is 0 or what? Yeah, this is 0. So 7 plus 2, 9. And 0 plus 2 is 2. This is 2. 2 plus 3, 5. 4 plus 2, 6. So this is 5. 32025. So 32025 should be the answer, which means A is the correct answer. Okay. So you need to just understand the algorithm properly, that what they are saying as a round. Otherwise, you will get confused. So they are saying that whenever you are changing the link, it's not a round. After the change in the link, you are having some round. That's what they are saying, right? Okay. Is this clear to everyone? Let me know if there is any confusion here. Now let's just see this linked question, which is question number 53 in the same year, which is GATE 2011. Let's just see this linked question. Now what they are saying is that, let's just see this question. So they are saying after the update in the previous question. See, after the update in the previous question means that I just updated N3, but they are saying you need to update all of them. Okay, this is just okay. This will not update N3. One iteration will update everything. You have to update N1, you have to update N2, you have to update N3, like that, right? So you have to update everyone, and then they are saying then the link N1 N2 goes down. You update everyone, which means that you will be having some other vectors here. Okay, after updation you will be having some vector for N1, you will be having some vector for N2, similarly you will be having some vector for N3, like that, right? N1, N2, N3, N4 and N5. So after the updation from the previous round, you will be having 5 different vectors then. So this is, let's suppose this is N2, N3, N4. You will be having 5 different vectors. Then you need to check that which one is the correct. Then what you need to do, this is same as the question number like previous question. The only difference is that first, this is the extra work that they have given. You have to update them. Then earlier also they were changing some cost, that's from 6 to 2. Now they are changing some cost, which is they are changing that to n1 n2, they are saying goes down, which means they are changing that from 1 to infinity. Earlier also they have changed this 6 to 2. So both questions are same, it is just that you have to do this extra work. Okay, and after the next round then you have to change that n1 to n2 the edge infinity, which means you will immediately update this to infinity, you will immediately update to infinity. Then you will be again seeing that again updating the vector, what will the cost to n1 in the distance vector n3. So they have asked the same thing, they have asked the n3 vector only. Okay, and they have just asked only one of the entry, they have only asked one of the entry here. They have reduced your task, they just think that you just give me one of the entry. Okay, first step is that you do the previous question completely, not just for n3, you have to do it for n1 n2 n3 n4 n5, and then you do it infinity. Then you have one more round and then you calculate this. That is the all step that you have to do for this particular question, right? Okay, so learn with me saying very easy question. Yes, I mean once you understand the concept properly, then it is very easy question. I completely agree with you. Okay. Now, since we are having, I mean, scarcity of time, so let me move to our last concept, which is link state routing. And if you have any doubt, you can just comment it out over the YouTube, and from the YouTube only we will be solving. Okay, I will solve personally all of your doubt on the YouTube. So if you have any doubt, you can comment here on the YouTube. So see, every comment of YouTube is either monitored by me or Deepak. There is no one else in Go classes. Either me and Deepak are there. So every comment, any technical reply, okay, anything that either me or Deepak does. Cool. So link state routing is basically saying that you need to flood your vectors to everyone, not just to neighbors. Okay, which means that E will be flooding its vector to every of the node, and A will be flooding to every of the node. Similarly, B will be flooding to every of the node. So everyone will be flooding to every of the node, right? So which means I say that link state packets looks like this. Initially, this is the initial configuration, where ABCD is having only the distances to the neighbors. Okay, ABCD is having only the distances to the neighbors, which is the initial configuration. Now you need to do what? You need to basically flood all of these link state packets to everyone, which means everyone knows about everyone else. So it will get converged very soon. In just one iteration it will get converged, but the one iteration itself is basically flooding. Okay, currently you might get confused that what is the sequence number and what is this age. So let me just remove it for now, just for 1 minute. I'm just removing it. I will tell you in a minute. Okay, I will tell you this in a minute. For now, let's suppose that these are the link state vectors. Okay, so suppose these are the link state packets. A is having this packet, B is having this packet. So basically you flood to everyone. Then at everyone you can apply the single source shortest path separately, and then you can get the answer, right? So I know that you already know that how to do these kind of questions. So basically what you need to do at A, since you will be getting all the vectors, these all the vectors are available at A, these all the vectors are available at B, right? All the vectors are available at C, so all the vectors are available everywhere at C also. So basically you can apply single source shortest path at every node, which means you can say at A you know the whole topology, right? At A you know whole topology, which means you know that what is happening with the network. So you know that okay, this A is connected to maybe B. I mean you can apply the Dijkstra at A, and then you can get to know that what is the answer that you will be getting at A. Like apply the Dijkstra at A, just like an algorithm question. Apply the Dijkstra at B, apply the Dijkstra at C. That's all. Now, most importantly in this particular algorithm, I want to talk about these two things, which are sequence and age. What are these two things? Because there could be a theoretical MSQ that they can ask based on the sequence and age. And most probably they, I mean, actually nobody can predict, but yeah, most probably they can ask, because I mean, they have asked DVR last year. Actually I cannot comment, but they may ask this LSR this time. So let's see what is the sequence number. See what is happening, that in the LSR you are doing something, which is basically you are having some, let's suppose these are some routers, and there are multiple paths. There could be multiple paths between two routers, right? I mean, let's suppose there is one path which is this one, there is one path which is this one, and there is another path which is this one. Let me use another color. There is another path which is this one. Suppose that this path is slow. Okay, this path is very slow, this path is slow, and this path is fast. You are sending some packet, okay, some link state packet using this path, you are also sending using this path. But since it is slow, let's suppose it is reaching to the node R, okay, or maybe R1, this is R2. So R2 is sending something to R1, or maybe let me call A and B. So let's suppose that this is B and this is A or whatever, right? So A is sending something to B. Then since this path is slow, then the packet that you are sending might reach sometime later. Let's suppose this is reaching after 1 day. Okay, this is reaching after 1 day. And this is reaching early. This is good that it is reaching early. All the communication can be done here. But since it is reaching after 1 day, then after 1 day we will get to know some LSP, some link state packet, right? Some LSP it will get to know. But this is very old. 1 day is too much in computer networks. I mean, like bits and bytes travels with the speed of light. 1 day is too much. I'm just giving some example of 1 day. Practically, it cannot happen. Even the 1 minute is too much. 1 minute itself is too much in computer networks. But just for the sake of understanding, so that it sounds practical, not the practical, but it sounds some human approachable. Okay, so I'm saying it 1 day. Otherwise, it is just 1 minute or 2 minutes of difference. Okay, so let's suppose it is very old packet and all the communication is happening using this particular way, but it is very old packet, and then B does not know whether it is old or not. It may use of this packet, but the current topology might be different, right? So that's why we have the sequence number. Sequence number says me that it is old packet or the new packet. So basically, I have the sequence number which tell me how do we know the LSP is new. Use a sequence number. Generate a new sequence number is newer. Greater the sequence number is newer. So basically, which means if I say some packet is having sequence number 100, some packet is having sequence number 2, then this packet they having greater sequence number. This is a new packet. I will say this is an old packet. Right? That's all. So I will do what? If I'm getting some sequence number, let's suppose 100. Let's suppose 2. If I'm getting some sequence number 2, and I have already seen sequence number 100, then I will discard this 2. I will get to know that okay, it is very old packet, right? That's why the sequence number is needed. I hope that is fine. But sequence number alone is not enough. There is something called age. Age is basically saying that if the sequence number is getting garbled, which means let's suppose that you have some packet which is having the sequence number 5, okay, and then because of some error, this 5 which is just 101, this 000, I mean binary, it is 00001, because of some error just one bit get changed, and then this is 10000000101, which means this 0 is, let's suppose, getting changed to this one. Then it is a very big number, right? Very big number. Then receiving end will think that it is very latest, because since the sequence number is greater, sequence number is very big. So receiving end, receiver will think, receiving node will think it is very latest. It is latest packet. So what will happen? That it will think it is the latest packet. So let's suppose this number is 6535354, some number, okay. Let's suppose this is a very big number, and receiver will think that it has just received a LSP that is containing a sequence number which is 65354. Now whenever it is getting LSP of sequence number which is lesser than this, which means like 6, 7, 8, 9, all of them, it will think that okay, see, I just have the latest one. I have the latest one and these are the old ones, right? But that's not the case, because that was earlier 5 that has been changed to this one, and it will discard all of this 6, 7, 8, 9, 6 till this point, right? It will discard all of the packets. It will think that I have the latest one, but it is not. This sequence number is not the 65354. So to avoid that problem, we have one field that is called age. So there are two fields. One is sequence number, another one is age. Age is saying that keep this LSP. Keep LSP for, let's suppose, some time, okay, for let's suppose 5 seconds only. After 5 seconds, whatever the sequence number you have, you just discard that LSP. Okay, that's what the age says. Which means, see, you can read it from here. If you are sending 5, that may change to 65450, but this age is saying that you just discard it after some time. Maybe after every 10 seconds, you just discard the information. so that you do not keep any errorness, like any error sequence numbers with you. Okay, so I hope you understood that why sequence number and age both are needed. Why sequence number is needed? Because I should be preventing the old packet. We should we should avoid old LSPs, right? Which means if there are two paths between A and B, and if one path is fast, this is fast. If this is slow, another path is slow, then let's suppose this is slow, then I should be avoiding the LSP from this. Avoid old LSPs, right? So sequence number will tells me whether it is new LSP or old LSP. Tells it is new LSP or old LSP, right? So I think now I'm audible, right? Cool. What I was saying that in the transport layer, like we will be starting the transport layer. I think that quickly let me know if this was covered. Okay, let me know if that LSP you have understood everything. Okay, just let me know quickly that have am I missed or you have not. I mean, you have missed something from the LSP or everything is covered. Am I audible? Was I audible till that point? So, so I was just saying that in transport layer, there are many implementation dependent things. Like this TCP is basically implementation dependent. Whether I mean there are different versions of TCP. I will tell you that you do not need to remember anything. I will make sure that your transport layer journey is smooth. Okay, you do not really need to remember whether this TCP version is this or what, or there are many things that are implementation dependent in transport layer, but I will make sure that nothing is basically you need to remember, because they cannot ask you something which is to be remembered. So whatever they have asked, that is basically just based on the intuition, or which is the fix in all the versions. So I will tell you what can they ask, because something which is the natural thing which is fixed in all the versions. Okay, so there are different versions of TCP, but you do not need to remember anything. And I have seen some YouTube videos and some instructors that they say that okay, just remember that this is the TCP version, or whatever, right? But you do not need to do it. I will make sure. So thank you everyone. Take care. Bye bye. So I will let you know that when we are going to conduct this transport layer class. Okay. So if we are going to cover it tomorrow, then I will let you know. Otherwise, I think that we will start with the algorithm. Then maybe later I will conduct this transport layer class, maybe a day after tomorrow, or somewhere I will find the time. But this transport layer is my one of the favorite topic, and I wanted to cover it, but since we are having the class of graph theory, that's why we will be covering it. So thank you everyone, thank you, take care. Please just put a comment. Okay, if you have understood everything, just put a comment that you have understood everything. If there is something that you want to give as a feedback, just let me know. Okay, put a comment definitely, because it just help us, it just encourage us to put more and more efforts.